Hi, and welcome to PostgreSQL Essentials, how to level up your data work in PostgreSQL. 15 years I've been a developer, a DBA, and a team lead. I actually didn't start my career with Postgres. I started as an Oracle DBA, and for the first couple of years, I mostly, crashed databases, corrupted backups, wrote horrible SQL. But after a while, I actually became good at this stuff. I learned from all of my mistakes and became a half-decent DBA. At some point in my career, I teamed up with another founder and developer, and we started this ticketing platform. We wanted to use open source tools, so naturally we went with PostgreSQL as our main data store. Now, this was a very, very long time ago, and since then we grew this platform to more than millions and millions of active paying users every month. And Postgres is right there at the core. So in this videos, I collected a few topics which I feel are essential for understanding Postgres and enjoying the benefits of Postgres. So to get started, we are going to talk about SQL, PostgreSQL, and present a very quick overview of Postgres architecture. Now, I promise it's going to be a very, very short section. In the second module, we are going to talk about common administrative tasks in Postgres. So what does it even mean? How to create tables, how to create views, how to create materialized views, how to refresh them, when should you even use them? We're going to talk about schemas, why they are useful, the search path, what can you do with it? So many things you would not imagine. We're going to talk a lot about importing and exporting data from the database using the copy command, and I'm also going to share a few nice tips on how to make it useful for large ad hoc reports. Something from my own experience. We're also going to talk a lot about the database as the source of truth, how to maintain your data, how to keep it clean. We're going to talk about data types. We're going to talk about constraints. We are going to talk about how to gradually add them, manage them in a way that would not compromise the uptime of your system. And finally, we are going to talk a little bit about users' roles and privileges, and I'm going to share a few nice tricks on a unique feature of Postgres that you may have not heard of. Finally, my favorite model, the third model, we are going to talk about the query optimizer, and we're going to talk about performance. We are going to start by presenting the path of a query, what happens from the time you click enter with your query on your CLI or DevTools, whatever, until you get results back. And we are going to briefly understand how the cost-based optimizer works, and we are going to see a lot of execution plans. We are then going to tackle a real-life scenario with different types of, we're going to build like a mini system and going to run different types of use cases on it and try to optimize them using different types of indexes. We are going to start by talking about a B-tree index, the king of all indexes, the one you always use. We are going to present different features of a B-tree index, partial index, inclusive index, function-based index, and understand when each one of these features makes sense. We are then going to talk about hash index, the ugly duckling of indexes in PostgreSQL. So useful, but nobody uses it. We are going to present a few scenarios where it makes perfect sense to use a hash index and when it can even outperform a B-tree index. Finally, we are going to talk about the BRIN index, block range index, which can be very useful for different types of payloads. For the end of this model, we are going to talk a little bit about a few misconceptions about indexes in Postgres and present a few best practices for using indexes and managing indexes over time. So the bottom line, what are you actually going to get from this training? First, you're going to get more comfortable with Postgres if you're not already comfortable with Postgres. You're going to learn how to perform different administrative tasks in Postgres, and not only what's in the documentation. You're going to get a lot of insight, tips, and tricks on how to use the different features and when they make sense. And finally, you are going to learn how to evaluate different aspects of database performance. Throughout the slide, you're going to see that we have a structured way of evaluating performance of different queries. So thank you very much and stay tuned for the rest of the videos. Hi, hello, and welcome. I want to start this model with a quick overview of SQL and PostgreSQL and talk a little bit about Postgres architecture. So let's start with SQL and PostgreSQL. SQL stands for Structured Query Language, and it's the main language of interacting with RDBMSs, Relational Database Management Systems, emphasized on relational, not to be confused with key value stores, document DBs, NoSQL, NewSQL, and so on. SQL goes all the way back to the 70s, and as far as I know, it's the main language to interact with RDBMSs. There's been a lot of attempts over the year to replace SQL with other languages, but I can't think of any successful attempt so far. SQL became a standard in the 80s. These standards, ANSI standards, define syntax and behavior, and most of the commercial databases and popular DB engines that you're using today comply with these standards to some degree. And that's actually a very good thing, because it means that if you know something in one database, it's probably portable to other databases as well, okay? So PostgreSQL. PostgreSQL is based on a project called Postgres that also goes way back to the 80s. It was originally named Postgres 95, and I guess that somewhere around 96, they figured it's not a very good name and changed it to PostgreSQL. So PostgreSQL is free and open source. This means that you can use it, you can install it on your machines and use it even for commercial purposes without paying. You can contribute code to Postgres source, but you don't actually have to pay for Postgres, which is great. If you look at the chart at the bottom right, this is the DB Engines ranking, which ranks different database engines over the years. And you can see the orange line for Postgres, which is gradually increasing over the years in popularity. And this means that Postgres as a database becomes more and more popular. So most likely you are in the right class. If we're talking about Postgres, I want to introduce you to some of the resources and tools that comes with Postgres. Some of them we are going to use throughout this class. So first of all, I want you to get to know Postgres documentation. I know that for many of the tools that you're using, there's probably bad documentation. That's not the case for Postgres. Unfortunately, Postgres documentation suffers from very bad SRE, which means that if you search something in your favorite search engine, you're most likely not going to land on Postgres documentation, which is very unfortunate, but factual. So my suggestion to you is, if you have questions and you can find a straight answer in the search engines, go check the documentation. It's a great resource, and you should definitely get used of using the documentation. The second tool that we are going to use throughout this class is PSQL. PSQL is the interactive terminal, the CLI for PostgreSQL. If you have Postgres installed, you have PSQL, okay? This is how you start it. You just type PSQL, and you get this prompt where you can start entering commands. So PSQL comes with its own help system. If you'll notice, in the terminal, if you hit /?, you're going to get a lot of information about the commands that you can run with PSQL. In addition to that, PSQL comes with a lot of documentation on SQL that you can use. For example, if you forget the syntax for delete, you can just hit /h delete, and you're going to get all the syntax for the delete command. Now, you don't actually have to memorize anything, because, and that's a tip that I give to all junior developers, use the autocomplete functionality in PSQL. It's great. You can just start typing something and then hit tab, and PSQL will autocomplete the command for you. So many of the times you're going to get exactly what you need. In other times, you might discover very cool features of PostgreSQL that you did not know about. I personally found a lot of very cool features this way. So this is it. In the next video, we are going to talk about Postgres architecture and terminology. See you in the next video. Okay, now that we know a little bit more about SQL and PostgreSQL, it's a good time to talk a little bit about Postgres architecture. Now, the purpose of this class is not to go too deep into Postgres architecture, but nonetheless, I believe that there are some things that you need to know about Postgres if you want to work with Postgres, at least the terminology. So let's start with a cluster. A cluster is basically a Postgres installation on a server. Inside the cluster, we can have multiple named DBs, and the cluster defines the users, the roles, and their permissions. So a database, when we say a database, we basically mean a designated storage area on the file system that contains the definitions of our database objects. And when I say database objects, I mean tables, indexes, sequences, views, materialized views, and so on. A database is owned by a single user. Remember, defining the cluster. So a user in Postgres is used for both authentication and authorization. When we connect to Postgres, we need to authenticate with the user. And once we're in, the permission system controls what we can do with this user. We have an entire video devoted just for users and permission, and we are going to talk a lot about users and permissions. So Postgres uses a client-server architecture. This means that a client application establishes a connection with the database server. Now, the database will allocate a server process for each connection, okay? You can have multiple connections at the same time, and you can see how much by executing the command show max connections. Now, before I move on, a lot of the other databases that you're probably familiar with comes with their own connection pool. Postgres, unfortunately, does not have a built-in connection pool. This means that if you're using Postgres just for personal use, you're probably using one or two connections, that's fine. If you're using Postgres for analytics, you might have a few dozens very active users, and Postgres can definitely handle it. But once you start having, for example, using Postgres as a backend for an OLTP system, and you have lots of concurrent connections, this is probably the point where you need to consider whether you want to use an external connection pooler. Okay, so the most popular connection pooler for Postgres, as far as I know, is called PG Bouncer. So if you're using Postgres as a backend for an application that uses a lot of concurrent connections, you should definitely look into connection pooling. So when we create a connection, we said that Postgres allocates a certain memory to every server process. So the memory areas in Postgres can be divided into two categories. The first one is the shared memory, which is used by all server processes, and the local memory, which is used by each individual connection. Let's start by talking about the shared memory area, the shared buffers. The shared buffers is the most important part in Postgres memory area. It's basically a huge cache. If you ever use Postgres, you probably know this scenario. You execute a certain query. It takes a bit of time to complete, but then you execute the query again, and suddenly it's very, very fast. The reason for that is most likely that the first time you executed the query, you executed it with a cold cache. The data was not in the cache. But once you executed the query again, some of the data was available in the cache, which made it a lot faster. So you don't have to actually manage which objects and which table blocks or index blocks are in the buffers. Postgres is doing that for you using different types of algorithms. But if you want to see the size of the shared buffers, the default is 128 megabytes, and you can execute the command show shared buffers. Now, depending on your use case, you might want to increase this size based on your use case and the resources that you have available whenever you have this Postgres installation. So that was the shared memory area. Let's talk about the local memory area, which is allocated for each individual server process. Whenever we establish a connection to the database, Postgres will allocate a local memory area, which is just for us. You can imagine, obviously, that when we have a lot of concurrent areas, it requires a lot more memory. Okay, so the first memory area, local memory area, which is most important, called the work mem. This area, the work mem, is used for sorting in hashes, in hash tables, which are very frequently used when you run SQL. For example, when you do a hash join, you need some memory area to store the hash table. When you do a merge join, you need to do a sort, which uses some intermediate data structures in memory, and you need memory for that. So the default size is 1 megabyte, and after 1 megabyte, Postgres will be forced to go into disk. So if you have a lot of very small transactions, 1 megabyte might be suitable, but if you have big workloads, usually analytical workloads that require lots of joins, lots of sorting, lots of hashing, it might be a good idea to increase the work mem. The second memory area, the local memory area, is called the temp buffers. It's used for storing temporary tables, since it's less likely for concurrent transactions, concurrent connections to create temporary tables in memory. The default size is a bit bigger. And we have also the maintenance work mem, which is used for administrative tasks like vacuuming a table, vacuuming an index, or create index operations. You can see that the default size is much bigger because once again, it's very unlikely for a lot of connections to do create index at the same time. So the default size is slightly bigger, okay? So the last part I want to talk about is the WAL, the work ahead, write ahead log, okay? This is a very important component in Postgres architecture. We are not going to talk a lot about it, but I thought that you should at least know what it's used for. So the write ahead log, the WAL, is basically a ledger, a log of all the changes that were made to the table. So this log of changes is very useful and crucial for a lot of the database operations. For example, if you had a disaster and the database crashed, when you bring the database back up, the PostgreSQL would use the WAL to restore the database to its state as of the last committed transaction before the crash. Okay, so that's one use. If, for example, you take this WAL, this log of changes, and you send it to another server and apply these changes to another database, what you get is an identical database with a slight lag behind your database. This is called a replication, which you can implement using the WAL. Another nice use of the WAL is point-in-time recovery. Imagine this scenario. You just deployed a version of your application, and after 30 minutes, you suddenly found that there's a disastrous bug in the application which caused the application to completely corrupt the data. And you want to roll back the database to the state it was 30 minutes ago. So using the WAL, under some circumstances, you can do that. It's called point-in-time recovery. So this is it, a quick recap. We talked about architecture and terminology. We talked about cluster. We talked about database. We talked about user, client-server architectures. We talked about the different memory structures, the shared memory, the shared buffers, and the local memory areas, which are designated for each individual connection. And we talked very briefly about the WAL. So this concludes our introductory model. And in the next model, we are going to dive into code and start doing a lot of things with PSQL. So stay tuned and see you in the next video. Hi, in this chapter about administrative tasks, we are going to talk about how to manage tables and views, how to get data in and out of the database using the copy command. We're going to talk about integrity, how to maintain data integrity to keep the database clean as possible. And we're going to talk about how to manage users and rows. So let's begin. I want to start by creating a database. So if you recall, the database is basically a designated storage area that contains the definitions of our database object. So let's start by creating a database, and we can do that by using the create database command. As you can see, create database with the name db1 owner Postgres. This will create a database called db1 owned by the user Postgres. To connect to this database, we can use the /connect command with the name of the database db1. We can see a nice prompt. You are now connected to database db1 is user Postgres. This tells us exactly what database we are connected to and with which user. You can also see that PSQL prompt changes with the name of the database. Previously, it was Postgres, the default database that comes with every installation, and now it's db1 because we are connected to db1. Now, if for some reason you want to create a database from the command line, Postgres comes with a command called createDB. It works exactly the same way. CreateDB, db1, name of the database, minus capital O, which stands for owner, and the name of the owning user, in this case, Postgres. Sometimes it's more useful and more comfortable to create databases directly from the command line, for example, scripts, CI, and so on. So, if we want to see a list of all the databases that we have in our cluster, we can use the command /l. And we can see that we have db1, which we just created. We have Postgres, which is the default database that comes with every installation. And we have a couple of templates, which I personally never used. So, in a relational database, data is stored in tables. Tables have columns. Tables can define constraints, and tables can have indexes to speed up access to their data. To create a table in Postgres, we can use the createTable command followed by the name of the table. In this case, createTable users. Inside parentheses, we give a list of column name, ID active name, and their type, int, boolean, text. So in our case, we have a users table with an ID column, which is an integer, active column to indicate if the user is active or not, which is a boolean except true or false, and we have the name type text, which is unrestricted text. We are going to talk about some of the other aspects and some of the other elements in this createTable users, and we are going to add a lot on this table throughout this class, but let's start with something simple. As you can see, after we execute the command, you get a nice feedback says create table, which means you just created a table. Congratulations. Now, sometimes it's useful, especially in scripts, to create a table only if it's not already exist. You can do that using createTable if not exist. Okay? Once again, great mostly for scripts. So just like we can create a table, we can also drop a table using the drop table command followed by the name of the table. In this case, drop table users. So once again, very useful in scripts. Sometimes we want to drop a table only if it's not already exist. This is useful because sometimes you write scripts to create tables. Now, if you create a table that already exists, you are going to fail. If you are trying to drop the table before you create it and the table does not exist, you're going to fail. This is why drop table, if not exists, is useful. If the table exists, it's going to be dropped. If it does not exist, it's just going to fail silently. No problem. Once again, very good for scripts. Now, after we created the table, it can be useful to inspect what we just created. We want to view the contents, the definition of the table. And we can do that using the /d command, which I imagine stands for describe. So /d with the name of the table users, and we get a very useful output. We are going to come back a lot to this output, and we are going to see how the different things that we do on the table affect this output and manifest in this output. But for now, let's see what we have. First, we have the column names. We have ID, active, and name. Then we have the type column, which tells us what is the type of each column. In this case, integer, boolean, and text, exactly like we defined it. We then have the nullable column, which we are going to talk about later on, and the default. If you see at the bottom, we have another section for indexes. We are going to come back to that as well. But as we add more into this table and make this definition more elaborate, we are going to see more sections being added at the bottom of this output. Now, if we want to list all the tables that we have in the database, and this is very common, especially when you land on a new database that you're not familiar with, so you can use the /dt command and then which is going to give us a list of all the tables. Right now, we only have the table users. Now, the /dt command is also useful for searching tables by name using a wildcard. For example, we can search using /dt foo star for all the tables the name starts with foo. In this case, we have none. We can search for all the tables that start with u using /dt u star, which will give us our users table. Now, if your team has a naming convention, this can be extremely useful. If you're starting a new project, I highly recommend you devote at least a couple of minutes to come up with a good naming convention. So finding your way around the database using the names of the objects would be as easy as possible. So after we define the table, sometimes we want to make changes to the definition of the table. Obviously, if the table contains data already, we can't just drop and recreate it. So for that, we have alter table command, which allows us to change the definition of the table. Let's say, for example, that we want to set a default value for our active column. This means that if someone tries to insert a user without explicitly specifying the value for active, we want to set a default value, in this case, true. And this is how we do it. Alter table with the name of the table users, followed by alter column with the name of the column. In our case, that's active. Set default and the value true. We get a nice prompt saying alter table, meaning the command was successful. And then once again, we describe the table using /d users, and we can see the highlighted row in the output that now the default value for active is true. Now, when someone tries to insert a value without explicitly providing a value for the active column, the value is going to be true. If you look at the insert statement in the slide, you'll see that we're inserting a user called Aki Benita, but we don't actually provide a value for active. However, when we select from the table, we can see that the value was set to true. This is because we set a default value on active. Setting good default values is a very good and effective way of making it very hard for people to make horrible mistakes. So take the time to set default values that make sense. So if you remember, previously we talked about the WAL. The WAL is a ledger that keeps track of all the changes that were made to the database. Now, this WAL is extremely useful. It's used for so many things. However, this WAL, maintaining a log of all the changes, naturally incurs some kind of overhead, because every time I make a change, I also need to write it to the WAL. So under some circumstances, you might want to just not log changes to the WAL and make things a bit faster. Now, you need to be very careful with that, but it can be useful. Some of the situations where I found personally that it can be useful to create a table that is not logged to WAL is, for example, if I use like a temporary or intermediate tables for some ad hoc analysis, in case of disaster, I don't need this table. In case something bad happens, I don't need this table. If I have replications, I know I don't need these tables to be replicated. This is just like a one-off, a disposable table. Another very common use case for using unlocked tables is sometimes you implement ETL processes, and throughout this ETL process, you need to use a lot of intermediate tables. Now, these intermediate tables are not important on their own. They're just facilitating the process. So you can gain a little speed up by defining these tables as unlocked. You can see create unlocked table, and changes made to this table will not be written to log, which means it removes the overhead of the WAL, so things are going to be slightly faster. However, in case of disaster, you won't be able to restore the data. So do not use unlocked tables for important information. Also, because data is not locked to WAL, the data is not going to be replicated. So if you have a replication, the data would not appear in the replication. So let's talk about views. Views are basically named queries, okay? The important thing to note about views is that the results are not materialized. Every time I access the view, it's identical to just querying the table, okay? So let's create a view using the create view command with the name of the view. In our case, we want to create a view with the IDs and the names of all the active users. So we issue the following command: create view active users, that's the name of our view, as followed by a query. In this case, select ID name from users where active, okay? So now we can access the view just like we query a table. So let's start by inserting an inactive user into the table. Let's call him Bob Bar, and we set the value of active to false. If we query active users, we can see that Bob Bar is not in the results of the view. We only get Aki Benita, which is the active user, okay? If we query, if you see the second query there, select star from users, we can see Bob Bar, but Bob Bar does not appear in the view because the view includes only active users. Now, just like inspecting a table, we can also inspect a view. You can hit /D, but if you had /D plus, you also get the view definition at the bottom, okay? Which is very, very useful. Now, another variation on views is that sometimes you want to reuse a certain query within your session, but you don't actually need it all the time. Once again, it can be useful for things like ad hoc analysis or ETL processes, stuff like that. So you want to have like this named query, this view that you can access very quickly, but you don't want it to stay at the end of the session. So for that, you have temporary views. Temporary views you can create, and once the session terminates, for any reason, Postgres will automatically drop the view for you. Let's see an example. We can create this temporary view called inactive users, which selects star from users where not active. This is a view that contains all the inactive users. And then we can select from inactive users. We can see Bob Bar, the inactive users that we previously added. And then when we reconnect to the DB using /connect DB1, basically terminating the session and starting a fresh session on the same database, when we try to query inactive users, we get that the relation does not exist. And the reason for that is that inactive users was a temporary view, and when we terminated the session, Postgres dropped the view. Okay, so we talked about views, and we said that the results of the view are not materialized. Whenever we access the view, Postgres will just execute the underlying query, okay? So the more successful brother of views is materialized views, which is also a named views with one significant difference. The database would actually materialize the results of the query, meaning the database would execute the query and store the results in a table, okay? So to create a materialized view, we can use the command create materialized views followed by the name, users by active status _ MV. I personally like to add MV suffix to the name of all the materialized views to indicate that this is a materialized view and not an actual table that I can manipulate, okay? So create materialized views followed by the name as and a query. In this case, we want to get a count of all the users by the active status, okay? So now we can query this materialized view just like a table. Select star from users by active status MV, and we have one inactive user and we have one active user, okay? Now, when we executed this query, when we accessed the materialized view, the underlying table, the query was not executed. All the data is already stored in the table. Let's see an example. If I add a new user, let's call him Jax, and this user is inactive. If I query users by active status, my materialized view, I can see that the results are not changed. So I just added an inactive user, but the results of the materialized views are stale. They are not up to date. If I want to refresh the results of the materialized view, if I want to tell the database, hey, your results are stale, please recalculate the result and store the fresh result, I need to explicitly issue refresh materialized view with the name of the materialized view. Only after I do that, you see that I can query the table and the data is up to date. Okay, so this is extremely important to understand about materialized views. They are not updated automatically. You need to explicitly refresh them. And whenever you refresh them, Postgres will go and re-execute the query and store the data in the table. If you want to see another example, if I delete the user jacks, query the materialized views, the results are stale. Only after I refresh the materialized view, I can query the mView again and I get the fresh results. Now, there's a lot of hype around materialized views, especially about maintaining aggregates in the database. So I just wanted to say something about it. There are two ways of refreshing materialized views. The first one, the one that we just saw, is called complete refresh or full refresh. This basically tells the database, re-execute the query, store the result. This is how Postgres works. However, there is another way of maintaining materialized views using something called fast refresh or incremental refresh, which basically only apply the changes to the materialized views since the last time it was refreshed. Now, and that's important, it's not available in Postgres. It's not available in Postgres. There are other databases like Oracle that has this, but Postgres does not. There is an extension called PGIVM, which stands for Incremental View Maintenance, that implements something similar to fast refresh in Oracle. But I just wanted you to know that this is something that Postgres is talking about, okay? Everyone realizes that this is something that can be useful for people working with Postgres. So for now, we don't have incremental refresh of materialized views. We have an extension. I would even go as far as saying experimental extension at this point. But once again, something that should be mentioned if we're talking about materialized views. So remember, Postgres is only supporting at the moment complete refresh. So quick recap before we move on to the next video. We talked about, we saw different ways of inspecting and describing database objects, tables, views, and so on using PSQL command /d/d+/dn and so on. And we saw how to create a table, a view, and a materialized view. In the next video, we are going to talk about schemas and the mysterious search path. See you in the next video. Hi, in this video, I'm going to talk about schemas and the mysterious search path in Postgres. So schemas are basically namespaces within your database. Inside your database, you can have multiple schemas and you can have different database objects like tables, views, and materialized views by the same name in different schemas. If you want to think about your database like a file system, then schemas are folders and directories. They are a way of organizing all the database objects inside your database. So when you create a new database, there's a default schema called public created for you. So let's go ahead and create a schema using the create schema command followed by the name of the schema, in this case restricted. If we want to list all the schemas in our database, we can use the command /dn. And as you can see, we have the restricted schema that we just created, and we have the default public schema that exists in every database. Now, if you recall in the previous video, we created a users table. So now we want to create a table to contain the credentials of these users. For example, their passwords. Now we want to make it very clear that this table can contain sensitive information. So we create the table inside the restricted schema. To do that, we use the create table command following by the fully qualified name of the object we want to create, in this case, restricted credentials. This will create the credentials table inside the restricted schema. So we include an ID, that's the primary key. We have a user ID that references the primary key of the users table. We are going to come back to that when we discuss constraints and foreign keys. And finally, we have the password. Now, For demonstration purposes only, we store the password here in clear text, but in your real application, you should never store passwords in clear text. So after we created the restricted credentials table, we can query from this table using the fully qualified name. Select star from restricted credentials. So let's pause for a minute and talk about how we reference objects in the database, okay? So there are two ways of referencing objects, database objects. And when I say database objects, I mean tables, views, sequences, materialized views, and so on. So we have the qualified and the unqualified name. The qualified name includes the name of the database, the name of the schema, and the name of the table. In our case, that would be DB1 restricted credentials. This is not very common. It's not very common to include the name of the database in the name. So what you would usually see is the name of the schema and the name of the table. In our case, restricted credentials. When we created the table, we used restricted credentials. When we then query the table, we use this qualified name. There is, however, another way of referencing objects in Postgres using an unqualified name. This is just the name of the database object, or in this case, select star from credentials. So the question now is, when we use unqualified names, names that don't include the database and the schema, how does the database knows which object we are referring to? So for that, the database has something called the search path, okay? So the search path is basically a list of schemas that the database would look for objects when we reference unqualified names, okay? So let's start by looking at the default search path. We can issue the command show search path and we get a list of values. The first value, the first schema is a special value, $user. This value resolves to the name of the currently connected user. If I'm connected to the database with user app, this is going to resolve to app. If I'm connected to the database with the user Aki, this resolves to the value Aki. The next schema on the list is public. This is the default schema that we have in every database. So let's look at a few examples. If user app is now connected to the database and the user app references the unqualified name users, the database would look for app users because the user is app, and that's the first value on the search path. So app users does not exist, so it would go over to the next value, in this case, public. Public users exist, so this is what the unresolved name user is going to resolve to in this case. If, for example, our search path contained another value, for example, restricted, if the user app references the table users, the unqualified name users, the database would first look for restricted users, then app users, and finally public users, okay? So in our case, if we select star from credentials, okay, the database is not going to find our objects. We need to use the qualified name restricted credentials. Another option, as we just saw, is to add the name of the schema to the search path. So we can change the search path using the set command. So set search path to, and now we add restricted to the list. Now, when we select star from credentials, the database knows to look for the object credentials in the restricted schema. So this might be a bit confusing and you're asking yourself, okay, this is great, we get it, but what is this even useful for? Why would I want to reference different objects by the same name? So as it turns out, it can be very, very useful. So I want to present to you two very common use cases for using the search path and schemas in Postgres. So the first use case is implementing multi-tenancy. If you have usually a large SaaS applications with different customers, sometimes it's necessary to create a separate environment for each customer. One way, customer or tenant, of course, yeah? So one way is you create a separate database for each customer, for each tenant. This has the advantage of keeping data completely separate, but there's also, it incurs a lot of overhead for maintaining different databases and maintaining similar data across many databases. This is often called the silo. The other approach to multi-tenancy is to have just one table, and for all the tables that contains data for multiple tenants, we have this tenant ID column, and then the application can filter the data based on the currently connected user. So this has some benefits. It's significantly easier to maintain this type of setup. However, it is a bit more risky to have data leaking between different tenants. For example, if there's a bug in the application, a developer forgot to add the where clause to filter on the tenant, and so on. So one way is completely separating the database, called a silo. Another option is to share everything and apply these restrictions at the application level. Another option in between is using the same database for all the schemas, but keeping tables that needs to be tenant specific in a schema named after the tenant. So if you look at the diagram at the bottom right, you'll see we have two tenants. We have tenant A and tenant B. So we want to keep the tenant orders separate. So we create a schema for tenant A and we create a schema called tenant B, and we put the orders table in each of the tenant's schemas. This way, when tenant A connects to the database with the user tenant A and selects star from orders, the database is going to query from tenant A orders table. When tenant B does the same, tenant B is going to, the database is going to resolve the name order to the orders table in tenant B's schema. Another nice feature of this setup is that you can have shared tables like information about brands, categories, products in the public schema, and all the tenants can share this information. So you only have to maintain it in one place. Okay? So this is how you implement multi-tenancy with the search path and schemas in Postgres. Another common use case for schemas and search paths in Postgres is for implementing data migrations. Sometimes you want to make changes in the database, but you don't want the application to notice any of the change. So you want to fool the application into thinking the data has a certain structure until you finish your migration. Let's look at an example that would be the easiest to demonstrate. Let's say that we want to add a date joined column to our users table. This column should keep track of when the user logged the first sign up to our service. Now we can populate this data immediately because we don't have this information. So when we add this column, this column is initially empty. The value is null. Now we don't want the application to see missing values. We want the application to see some value. So while we populate this field, maybe we need to go and parse application logs, extract this data from somewhere. Maybe it takes a lot of time. And in the meantime, we want the application to see something. We don't want the application to have to handle missing values. So what we can do is we can create a schema called app user. This is the user that the application is connecting to the database with. So we create a schema with the same name, app user. Then we create a view inside the schema. You can see create view app user user, and we get the ID, the active, the name from the users table, and we use an expression on the date join. So when date join is null, we use the special value, the 1st of January 2020, okay? Then we grant permissions on the view to the app user user. We are going to talk about that when we talk about users and permissions. And now, when app user is connected to the database and referencing the user's object, for example, select star from users, the app user is going to query the view that we just created. And as you can see, it got the dummy values that we set for the date join column. So this is the second common use case for search path and schemas in Postgres. There are many, many more use cases. These are just two of the ones I'm familiar with and implemented in the past. So another schema that we have in our database is called PG Catalog, and it contains tables with metadata about our object. Let's look at a few examples. We have a table called PG Table that contains information about our tables. For example, if we select star from PG tables where the table name is users, this is our table, we can see the name of the schema, public, the name of the table, the owner, whether it has indexes or triggers, and so on. Another useful table is PG indexes. For example, we can query for all the indexes on the users table. We can even get the index definition at the bottom. Now, if we want to query all database objects, a very useful table is PG class. As you can see, we can have different types of objects here. We have tables. These are our relation tables. We have indexes, sequences, V for views. We have materialized views and many different types of database objects in the PG class table. Now, there's many tables in the PG catalog schema, but there are a few tables that I think everyone should know. So the first one is PG stat activity. This table contains information about the current activity in the database. So when someone pops into your office saying, "Hey man, the database is super slow, what's going on?" Then what you do is you select star from PG stat activity and you get everything that's being executed right now in the database. Okay, this is a great entry point for analyzing why everything is so slow. Other tables which are very interesting and super useful are the stat tables. You have PG stat table, index, and PG stats. These tables contain statistics that the database maintains on your tables, your indexes, and even on table columns. We are going to talk about these tables when we talk about the optimizer, the query planner, and when we view different execution plans in Model 3, I think. I want to share with you a tip for exploring the information schema, because there's a lot of tables there, and sometimes you are having trouble finding a piece of information. So one trick that I found is sometimes when you're executing a PSQL command like /d, for example, and you see a useful piece of information, you want to know where this information came from. So what I found is that you can set this parameter in PSQL. You set echo hidden on. And this way, when you execute a PSQL command, it will give you the actual query that PSQL executed behind the scenes to find the information. So you can see, for example, when I do /d foo, you can see the actual query that PSQL used to find information about foo. You can see that it tried to query PG class, for example. So this is a very useful way of exploring the information schema in PostgreSQL. So, quick recap before we move on to the next video. We talked about schemas in Postgres. Remember, we said that if you imagine the database like a file system, a schema is like a directory, like a folder. A schema is basically a namespace. It's a way of organizing your database objects and controlling access to them. We talked about how to reference objects using qualified and unqualified name, and we described how the database is using the search path to resolve unqualified name. We also described different use cases of when this might be useful. And finally, we talked about metadata tables, the catalog that we have in every database, data about our data. So this is it about schemas and the search path. In the next video, we are going to talk about the copy command and how to get data in and out of the database quickly and efficiently. So thank you and see you in the next video. Okay, hi. In this video, I want to talk about one of the most common tasks that all of us are doing on a daily basis, maybe even several times a day, and that's getting data in and out of the database. Now, I'm not talking about getting data in and out of the database for backups or ETL processes. I'm talking about actually producing reports from the database. So Postgres has a very useful command called copy, which allows us to export and import data in text, CSV, and binary formats. Okay? And one of the main use cases of copy, which I personally found, was it's very good and producing ad hoc reports, okay? So let's walk through the steps here as I introduce you to the copy command. So first of all, as I promised in the beginning, PSQL comes with a very nice help system. So we can all start by issuing /h help copy and get the entire syntax for the copy command. So let's start with an example. We have this target table called users, right? /d users. We created that table in the previous videos. We have ID, active, and name. And we have this CSV file, okay? So first of all, you may notice that I use /! which is a command that allows you to execute commands in the host environment. Meaning, if you're using Linux, for example, so you can use /! And cat. So this will execute an OS command. In this case, we want to review the contents of the user CSV file, which we want to import into our table. We can see that we have an ID, active, and name column, and we want to import that into our CSV table. So let's start by issuing the command /copy with the name of the table users from and a path on my workstation. In this particular case, that would be /temp/users CSV. Okay. Now, if you notice, we get an error, a strange error saying that we have invalid input syntax for type integer, ID, active, and name. So that's a bit of a strange error. But what happens is that PSQL treated the first row of data, which is actually headers, as data. And that's a mistake. So if we want to tell PostgreSQL that the first row is headers, what we need to do is we need to issue the command this way, /copy users with the name of the table from path on my local machine, in this case, temp user CSV, with CSV, that's the format, and then header, which indicates to PSQL that the first line should not be treated as data, but as headers. And once we do that, we get a nice prompt saying copy 3, which means PSQL just imported 3 rows into the table. If we select start from users, we can see the rows we just imported. So that's great. We see Aki, Bob, and Ben all in the users table. Now let's try to import another file. Once again, /! users to CSV. This time we want to import users to CSV, and that's the content. We have active name and ID, and we have 2 users, Andres and Jonathan. Now, if we try to copy users from temp users to with CSV header, we once again get an error message saying that, let's see, syntax for type integer T. So Postgres is trying to get the value T into a column with type integer. Now, if you notice, the order of the columns in the file users to CSV is not the same as the order of the columns in the table. The columns in the table are ID, name, and active, but in the CSV, that's active, name, and ID, so it's backwards. So if we want to import this file into our database, to our users table, we need to let Postgres know what order of the fields. So copy users, and then we say the orders in the file are active, name, and ID, so match these columns against the table. Once again, from users to CSV with CSV header, we get copy 2, meaning Postgres imported 2 rows into the table, and we can see Andres and Jonathan right there at the bottom. That's great. Congratulations. You now know how to import data into the database. Now, just like importing data, sometimes it's necessary to export data from the database. So let's start with a simple scenario. We just want to export all the data from the users table to some file on our local system. So we start with /copy users, the name of the table. This time, instead of from, we use the word to. So copy users to and a path on my workstation, in this case /temp/all users CSV with CSV headers. This indicates to Postgres that we want the file, the output format to be CSV, and we want Postgres to include the headers in the output. So we can see copy 5, meaning that Postgres wrote 5 rows to the output. So let's review the contents of all users CSV. We can see a line of headers, ID, active, and name, followed by all the users in the users table. That's nice. So exporting entire tables is useful, but more often than not, we want to export the results of a query, right? So for that, instead of providing the name of the table, we can provide a query inside parentheses. So let's take this, for example. We want to export the ID and name of all the active users to a file called active users CSV. So we do that by issuing the command /copy, and then inside parentheses, we provide our query. In this case, select ID name from users were active. And to a path on our workstation, in this case, temp active user CSV, with CSV, that's the format, headers to indicate that the first row should be the headers, and the output is copy 3, meaning Postgres exported 3 rows into the file. If we review the contents of active users CSV, we can see our 3 active users, Aki, Ben, and Andres. So this is great. This is amazing for ad hoc reports. Now, let's talk about an actual problem, okay? So let's say you want to produce a report for a big query. Let's take this query, for example. This query produces a list of users, IDs, names, and how many credentials they have in their in our system. So we have like, I don't know, 5 lines here. It's quite big. It won't fit in just, one line. So we say, no problem. We just use copy, and we start typing. So we type /copy. We open parenthesis and select ID, name, count as credentials. We hit enter, and then we get this very, very strange message saying parse error at end of line. So this strange error is because the /copy command is unable to accept multiple lines, okay? That's a very strange limitation, but it's true. So /copy cannot accept multiple lines, but I have a very big query and I want to export the data. So what can I do? Okay, so let's start with the first option. Okay, so the first option would be just write the entire query in a single line. So this will work, but let's be honest, that's terrible. I mean, this is not maintainable. Nobody wants to write like that. Also, you probably didn't just write the query. You probably copied that query from somewhere else. So this is absolutely terrible. So we don't want to do it. It works, but we don't want to do it. Confession, I once took a very long query and tried to inline it this way just to get it copy to export the result. And let me tell you, it's not that simple. So the next solution that I personally came up with is let's use a view, right? And not just a view, let's use a temporary view. So we create a temporary view. I called it copy me with the query and no problem, including multi-lines there. And then instead of copying the query, I use the temporary view. So I do /copy, select from copy me to whatever file I want, and no problem. And as a bonus for the temporary view is that once I terminate the session, Postgres would just drop the view. So I don't even have to do any cleanups, okay? So that's a fairly good solution. The problem that I had with it is that it involved 2 steps. And when you wanted to do a lot of back and forth with the query, it became a bit tedious to always create or replace the view. So I was looking for a different solution somewhere, somehow, that I would be able to just quickly produce reports from the database to CSV formats, just so I can, get things done. I don't want to do it so trivial. So I ended up finding a very, very cool trick, and I'm going to walk you through this trick. So the copy command actually has 2 variations. You have the copy command, which is executed on the server, and you have the /copy command, which is actually a PSQL command with exactly the same API as the one on the server. Okay, I know it's a bit confusing, but copy is like a server command. It can produce reports to directories on the server. But I don't want data on the server. I want data on my workstation, right? So for that, I'm using /copy. So /copy is just like copy, but it's a client command executed by PSQL. So what you normally want is /copy. Unfortunately, /copy, as we've seen, cannot accept multi-line. However, the server copy can accept multiple lines. So I can do something like that with copy, okay? So I do copy, open parentheses, provide a big query, and then I can export the results. The problem is that I can produce reports to standard output, right? So I can use the server side, the server copy command, and I can tell, instead of outputting the results to some directory on my client, I can tell the server copy command that I want the results to standard output, which basically means I can see them on my terminal. Okay, so how is that useful? I mean, I don't really want to like copy and paste into some text file and, and call it whatever CSV. I want it to be, directly go into some CSV file. So how is this useful? Well, as it turns out, PSQL has an option to direct standard output to a file. Basically, whatever you see on the screen can be directed to a file. This option is /G. As you can see, execute query and send results to file. Okay, so if we take these two together, check this out. We use the copy server command to provide a multi-line query, and then we direct the output to standard output. You can see that to std out, okay? And then we use the /G command to direct standard output to a file on my local machine, in this case, report CSV. And as you can see from the output, I just exported four rows from a very complicated query to a file on my workstation. Okay, so it took me some time to come up with this trick, but along the way, you learn the difference between server copy and /copy, and you learn a very cool trick with the /G command in PSQL. Okay, so copy is actually not limited just to file. You can actually use copy to process data from programs. So let's see an example. Let's say that you want to import stock prices directly from some online service. Let's say Yahoo Finance, okay? Because they happen to provide a public API that allows you to download CSV files with quotes. So let's start by preparing the table. We create a table called price, and we have the date, the opening, high and low and closing price, and we have the adjusted close and the volume, all floats, okay? So now we want to get data from some online file into our database. So check this out. We use /copy price because we want to import data into the price table from, and this time I say from program. And inside brackets, I provide the program to execute. So inside the program, what I'm doing is I'm using CURL to download a file from this URL. In this case, Yahoo Finance, and I'm getting quotes for QQQ, okay? And I specify the end with CSV header. So what you can see the output is, first, the program was executed and the file was downloaded. It was then directed just like a CSV, just like a local CSV into copy, and we imported 252 rows, okay? And if we select start from this price table, we can see that we get nice, clean data directly from a file online. So very, very cool. I think it's very cool. So one thing you need to know about copy is very fast, okay? It's probably the fastest way to get data into the database. It's faster than doing inserts. It's faster than doing bulk inserts. So if you need to load lots of data into the database, you should definitely consider using the copy command, okay? So a quick recap before we move on to the next video. We talked about using copy to import data and export data from the database. I showed you a nice little trick to export query results from the database using a combination of the server copy and the client copy command and the /gpsql command. And we also described how we can use copy from a program. And we also mentioned that copy is very, very fast. I personally, I don't know if you felt that, but I'm a big fan of copy. I've used copy all the time. It's very, very great. Okay, so that's it for copy. In the next video, we are going to talk about data integrity, how to maintain good and clean data in your database using various features. So see you in the next video. Hi, welcome. In this video, I want to talk about data integrity, which is an extremely important aspect of database development. Database is usually the very core of every system. You can have a lot of applications, different types of application, different types of users. You have developers, you have analysts, you have DevOps, sysadmins, infrastructure DBAs. They all interact with the database through various tools. You might have an application that you developed. You might have third parties, off-the-shelf applications that work with your database. Everyone is messing around with the data in the database, and it becomes increasingly important that the data in the database is clean as possible. One saying I'd like to mention in this context is garbage in, garbage out. Once you have garbage in the database, it's going to pollute all the other systems, rendering them basically unusable. So in this video, we are going to talk about different ways where you can define types and constraints to maintain the integrity of your data. So let's start with the first line of defense. That's the column types. We already used column types. If you recall our users table, we had an active column, and we defined this column as Boolean. So if, for example, we try to insert a user called Sue with value not a Boolean for a Boolean field, we are going to get an error from Postgres saying that not a Boolean is not a valid input for Boolean. So I know a lot of people like to use text for everything because it makes perfect sense and it's very flexible, but in fact, it can compromise the integrity of your data. So using types that make sense can go a long way in maintaining data integrity. So let's see some of the common types that Postgres offers. First of all, we have varchar n, which is restricted text, and text, which is unrestricted text. We have small int, and big int, which are integers at different sizes with different ranges. We have decimal range and double precision. We have date, which is date without time. We have timestamp, which is date with time, but without time zone. And we have timestamp TZ, which is date, time, and time zone. Now, unless your application knows and really aware of what it's doing with the time zone, what you most likely need for timestamps is timestamp TZ, okay? We then have byte A for binary data and Boolean, which stores true or false. In addition to the basic types, Postgres also comes with a variety of, I would say, exotic types. So you have UUIDs for storing, well, UUIDs. You have JSON and JSON B columns to store JSON data. So if right now you're using text field for JSON, if you switch to one of these JSON columns, JSON types, Postgres will be able to validate that the JSON that you're inserting is an actual valid JSON. We also have HStore, which is like key value. We have range and array types, and there's many, many, many more types. You can find them in the link. Now, it's very important to set restrictions that make sense. If you recall, previously, we used a text type for our name column. Text is unrestricted text. So if you think about it, it doesn't really make sense for, let's say, a name to be 1,000 characters long, right? It doesn't make sense. Even 100 sounds like a stretch. So maybe using text for our name column was not a very wise decision. So we can actually change that. If you'll notice, we can do alter table and then alter name, the column name, to type varchar 20. This means that now if someone tries to insert a value longer than 20 into the name column, they are going to get an error, okay? So now let's talk about different types of constraints that Postgres offers us to maintain our data integrity. The first one is not null constraint. So null is a special type of value that indicates no value or missing value. So if we want to make something required, we can add a not null constraint, or in other words, not missing, okay? So currently in our table, we have an active column which can accept either true or false. But the truth is that it can currently accept 3 values. It can accept true, false, or null. So if our application encounters a user where the active column is null, what is the application supposed to do? It means that the active status for this specific user is basically undefined. So we want to prevent this situation. We want to say every user needs to be either active or inactive. It can't be stuck in any type of limbo in between. So to do that, we want to make the active field required. So what we do is we alter table users, alter active, the name of the column, set not null. And if we describe the table, we can now see the nullable column in the output. And now it says that active type Boolean is not null, meaning we cannot insert a row into the table without saying if the user is either active or not. In this case, we are trying to insert the user foo and provide the value null, indicating missing value to active. So previously, we were able to do that. But now, with the not null constraint in place, we can't do that. Moving forward, primary key, a primary key constraint. A primary key is a set of fields that uniquely identify each row in the table, okay? So for example, in a students table, that could be student ID. In a citizens table, that could be national security number. Or in an airport, that could be a passport number, and so on. Or if the passport number can overlap between different countries, then the primary key can be country and passport ID, okay? So a primary key must be unique. A primary key must contain a value, meaning a primary key cannot be null. It's required by default. A table can only have one primary key, meaning you can have multiple primary keys in a table, but you don't have to have a primary key on a table. Okay, so you can either have one primary key or no primary key. Okay, and a primary key can consist of multiple fields, in which case it's called a composite primary key. So we already defined a primary key. If you recall, when we created the table, we used ID int. Okay, ID is the name of the field, int is the type. And then if you look at the end of this line, it says primary key. Okay, if we describe the table, we can see in the output several things. First of all, Postgres behind the scenes created a unique index. You see users PK at the bottom to enforce this constraint. So Postgres created an index to quickly make sure every time we insert a row that there is no other row with the same ID, okay? It also marked the column as not null. We did not explicitly say it's not null, but once we define the column as primary key, Postgres goes on and adds a not null constraint on the column. Now, sometimes it can be useful to have an ID column that is populated from a sequence. For example, order ID, transaction ID, log ID, and so on. There's no actual meaning for the ID. We just want an incremental value. So for that, we can use identity columns in Postgres. And if you notice, this is the part that says generated always as identity. What it does, it goes on and creates a sequence behind the scenes and uses the sequence to populate new rows as we insert data into the table. Now, a quick reminder to those of you coming from older versions of Postgres. In the past, prior to Postgres 10, there was a type called serial. This type serial did roughly the same thing. However, it was not compliant with ANSI, and starting at Postgres 10, this type is softly deprecated. So if you're starting a new project, do not use serial, use identity column. Use generated always as identity. Now, for these identity columns, there's an option to control, okay, how user-specified values are handled. So there are two ways that you can do that. The first one would be always, generated always as identity. This means that if someone tries to insert a value, insert a row into the table, and provide an explicit value for our identity column, Postgres is going to prevent that, okay? Another option is generated by default, meaning if a value was not provided, use the sequence to find the next value, okay? So why would you want to prevent someone from adding, explicitly providing values for IDs? If you imagine a transactions table, do you imagine someone inserting a transaction into the table and providing the ID of the transaction? It's kind of weird. Also, if your current sequence is, let's say, at 10, and someone goes on and insert a row with ID 11, the next time, now with ID 11, now the sequence is not aware of the fact that someone just provided the value 11, okay? So the next time someone would try to create a transaction, the next value of the sequence will be 11, and we will get a unique constraint violation. So usually you want to prevent users from explicitly providing values for identity columns. So let's see what it looks like. If we define our identity column as generated always, and someone tries to create a user, in this case, the user Jax, and provide the value 9999 for the ID column, we can see that we get an error saying that column ID is an identity column defined as generated always, meaning we cannot provide a value for that. However, Postgres was kind enough to provide us with a little escape hatch. What we can do if we really need to add this value, we can do insert into and then provide overriding system value, which tells to Postgres, I know that this is an identity column with generated always, but trust me, I know what I'm doing, accept this value. And now we can do that. Okay, so we talked about primary key. Now let's talk about a unique constraint. So unique constraint is used to make sure that one or more fields are unique, meaning we don't have duplicate values, right? So in our transaction ID column, transactions table, for example, we want to make sure that the transaction ID uniquely identifies a transaction. So this is a unique column, okay? So when we add a unique constraint, the constraint behind the scenes Postgres, we go on and create a unique B-tree index to enforce this constraint. So whenever we insert a new row into the table, Postgres is going to use this index to make sure that there are no duplicate values. So let's say, for the sake of discussion, that in our users table, okay, we want to make the name unique, okay? We can't have two users named Aki Benita. So in this case, it's kind of funny, but if you have a users table, you might have an ID column, which is the primary key, but then you have a username, which is supposed to be unique, and you have maybe an email that is supposed to be unique, maybe a cell phone number that is supposed to be unique, and so on. So for the sake of discussion, let's say that we want to add a constraint called users name unique to make sure that the name is unique. So we do alter table users, add constraint, user's name unique. I'm using very descriptive names here because these names show up in errors. And then I say unique name. So name is supposed to be unique. If we describe the users table, we can see at the bottom, okay, in the index section, we can see that we now have a new unique constraint. It's under the indexes section because behind the scenes, Postgres is using a unique index to enforce this constraint, okay? So now if we try to insert another Aki Benita, we are going to get an error saying duplicate key value violates unique constraint with the name of the constraint, and we get a very nice message saying the name Aki Benita already exists, right? So this is what a unique constraint does. Now, in our case, as we already discussed, it doesn't make sense for the name to be unique. I mean, I don't know if there's another Aki Benita out there, but I don't know, maybe there is, and we want to make him a user. So we don't want to enforce this constraint. So just like adding a constraint, we can also drop a constraint. So alter table users, drop constraint with the name of the constraint, user's name unique, and now we can have duplicate, we can add another user called Aki Benita. So we talked about not null, we talked about primary, we talked about unique constraint. It's time to implement some custom validation logic using check constraint. Let's say that in our application, we want to make sure that when we ask for the name of the user provides at least the first name and the last name, okay? So I know that there's a lot of common misconception about names, but let's just say that someone can have 10 names, but I want to make sure that there's at least the first name and the last name. So a simple way of checking something like that is to check if the value of the name contains at least one white space, right? Because if the name does not contain a white space, the user most likely provided just his first name or just his last name. Okay, so if we want to implement this custom validation logic into our table, we can use a check constraint. So let's see what it looks like. Alter table users, okay, the name of the table, add constraint, and this time it's it's very important to use a very, very descriptive name for the constraint. So we say must contain white space, okay? This is the name of the constraint, okay? And now the keyword check, and inside parentheses, we provide an expression that must evaluate to true for the validation to pass. So in this case, we say name like anything, white space, anything, okay? Now, if we describe the table, we can see a new section at the bottom called check constraints with the name of the constraint. So Postgres did some transformation of the expression, but it's the same expression. Now, if we try to insert a value without white space, in this case, insert into users value George, so George is just the first name, we get a check constraint violation. Now, in this case, the name of the constraint is extremely important because Postgres doesn't really know which of the values caused this constraint violation. So the name of the constraint should be very, very descriptive, okay? So let's talk about foreign keys. Foreign keys is a way of defining and maintaining relations between tables. Now, if you recall, when we talked about schemas, we created a credentials table to hold the passwords for our users, right? And we had a user ID column, okay? So this user ID column is supposed to be linked to the ID column in the users table. But right now, there is nothing that actually enforces that. There is nothing preventing me from just adding credentials to non-existing users, okay? So if we want to make sure that we don't add credentials for non-existing users, we can use a foreign key constraint. So let's see what it looks like. So we alter the table restricted credentials because we want to add a constraint. So alter table restricted credentials, add constraint with the name of the constraint. I like to use FK, foreign key constraints. It makes them easier to identify. And then we say foreign key user ID references user's ID on delete cascade. So let's break it down. So foreign key user ID says that the user ID column in credentials table references the ID column in the users table, okay? So if I'm trying to insert a user ID, a credential for a user ID that does not exist, I'm supposed to get a foreign key violation. So let's describe the credentials table, and we can see a new section added called foreign key constraints at the bottom. It's highlighted there. And we can see our user FK foreign key constraint, okay? Now, if we try to add credentials for user 99, this user does not exist, right? We get a foreign key constraint violation, which is exactly what we wanted. We can't add credentials for users that don't exist. Now, let's talk about the third part of the statement, which we ignored so far, on delete cascade. This section defines what should happen when I delete the user from the users table. What should happen to the credentials? So before we dive into the syntax, let's understand what we actually want. If I deleted a user, what I want to do with their credentials? I want to delete them, right? There's no reason for me to keep credentials for users that no longer exist in the system, right? So in this case, I want the delete to cascade. Or in other words, if the user is deleted from the users table, I want the rows in the credentials table to automatically get deleted as well. Now let's take another example. Let's say that I have a transactions table, and in this transactions table, I have a foreign key to the user, okay? Which is the user that made the transaction. Now, transactions are very important business information. They hold information like, who I billed, how much I charged, when I charged. I can't simply delete transactions. So the question is, if someone tries to delete a users with transactions, what should happen? Now, in this case, we can say that if someone attempts to delete a user that has transactions, we want to prevent the user from getting deleted, from being deleted, okay? And this is the restrict option, okay? Once we say on delete restrict, we say if someone tries to delete the parent object, the user, okay, and they have object in this table, then do not allow this deletion to complete, restrict, okay? So let's see Cascadian option, okay? We talked about restrict, now let's see Cascadian option. So we insert a user called Ben Smith. You can see that the ID for Ben is 8, it's active, the user Ben Smith is active. And then we insert some credentials for Ben, the user ID is 8, the password is secret. Now, if we delete from users where ID equals 8, that's Ben, we can see that Ben's credentials, the password was secret, also got deleted, okay? So this is what Cascade does. So data integrity, okay? One thing I want to, if there's one takeaway that you should take from that is that constraints are very easy to remove, but they are very, very hard to add. Okay, it's always easier to loosen constraints than it is to make them stricter. So my suggestion to you is always start with strict constraints and then loosen them as necessary. Now I want to talk to you about a little aspect of constraints that I think is important, okay? So let's say that we have a very big table and we want to add a constraint on this table, okay? In this case, we have 1,000,000 rows and we want to add a check constraint that makes sure that the name is less than 100 characters long. So we add a check constraint called name length LT 100 and we check that the length is less than 100. If you'll notice the timing at the bottom, okay? By the way, if we want to actually see timing information in PSQL, we can switch on /timing, which is what I did over there. So if we turn on timing and add this constraint to an existing table with millions of users, we can see that it took 10 seconds. And during that time, the table was locked. So if you are running a production system, this is unacceptable, okay? If you have millions of users, enough users for this to take 10 seconds, then you probably have a very active system and you can't afford 10 seconds of a table like users being locked. So let's see what's happening under the hood when we are actually adding a constraint. So the first thing that's happening is that the database would try to obtain a lock on the table. The next thing is for new rows that come into the table, we want to enforce the new constraint, okay? So we start enforcing the constraint for new rows. In the meantime, okay, now that we have some lock on the table and we enforce the constraint for new rows, we start validating all the existing data, okay? Only after we validated all the past data, we can say that the constraint is now valid and release the lock, okay? So let's say that I do have a very big table and I do want to add a constraint on the table, but I have to do it with minimal locking, with minimal interference to a running live system. So what if we can actually add the constraint in steps? So let's see what it looks like. We start by adding the constraint to the users table, alter table users add constraint, but we specify not valid. This means that we want to start enforcing this constraint on new rows, but we don't want to validate past data yet, okay? Now, as you can see, this is very, very fast because it just requires an instantaneous lock on the table to add the constraint definition and start enforcing the constraint for new rows. The next part is, now that we have the constraint in place and we start validating new rows, the next step would be to validate all the past data. We can do that explicitly by issuing alter table users validate constraint with the name of the constraint. Now, as you can see, this takes 11 seconds, which is roughly what the previous command took, okay? But because we did that in steps, the lock required by this operation is much more permissive than the previous one, okay? So once this completes, okay, we have a new validated constraint on the table, which is valid both for past data and validates new rows, okay? Now, another tip I want to share with you is that we talked at the beginning of this video about text and unrestricted text when we talked about types. But there's a nice approach that I like, and it goes like this. Since it's much easier to change a constraint like we just saw than a column data type, okay? What if instead of using varchar n, okay, instead of using varchar n, instead of using varchar 20, we use a text data type, which is unrestricted text, but we enforce the constraint using a check constraint. So check this out. Instead of using varchar 20 for the name, we use name as a text type, unrestricted text, and add a check constraint to make sure that the length is less than 20. In this way, if in the future we decide to make the check constraint bigger or smaller, it will be easier using the approach we just saw. Okay, so let's do a takeaway and a recap of this section. So the database is the source of truth. Garbage in, garbage out. If you have garbage in the database, it's going to go into all the other systems and pollute everything, okay? Database is the last line of defense. You have validation in the client side, you have validations in the backend, but eventually everything boils down to the database. If this is why I like to think about the database as the last line of defense. Once something got committed, it's a fact, okay? This is why data integrity is crucial, and this is why you need to use constraints. So if you need to have, a takeaway here, then constraints are good, use constraints. When in doubt, add a constraint. It's always easier to loosen constraints than it is to make them stricter. So we talked about not-null constraints as the way of making a field required. We implemented custom validation logic using check constraint. Remember, the name contains a white space. We made sure that we enforced uniqueness using a unique constraint, if you remember the name. We maintained relation between tables using the foreign key. If you recall, the user ID that references the user primary key in the users table, and we talked about delete cascade and delete restrict. We also described how to use identity columns for primary keys, and we talked about different techniques for adding constraints without much downtime, okay? So in the next video, we are going to talk about users, and we're going to talk about permissions and privileges. So stay tuned. Hi, in this video, I want to talk about users and privileges or permissions, depending on where you're coming from, okay? So let's start with creating a user for our app. Let's call the user app. So we issue create user app, and we set the password to secret. Okay, to connect with this user, we're using the /connect command, which we saw earlier, but this time we provide both the database DB1 and the name of the user. In response, we get a very useful message saying that we are now connected to DB1 as user app. So when we fire up PSQL, we can also connect from PSQL directly using PSQL -d DB1, the name of the database, minus capital U, the name of the user, and minus capital W will cause PSQL to prompt for the password. Now, a word of caution. Do not provide the password in the command line, because commands in the command line are stored in your history. So either add a white space at the beginning to exclude this command from history, or use the minus capital W command to prompt for the password. Okay, this is safer. So in Postgres, we have different types of privileges. We have object privileges like select, update, delete, truncate on a specific table. And we have system level privileges like can connect to database, can create a user, and so on. So if we want to check the current state of our connection, we can use the command /con-info, and we are getting a similar message to connect saying which database we are connected to and with what user. And we are now connected with our app user, and we try to select from the users table, and we get permission denied, which makes perfect sense because no one granted us permissions to view the contents of this table. So if we connect to DB1 as Postgres, we can grant select on users. Okay, we want to grant select on the users table to the user app. And once we do that, we can connect to DB1 with the user app, and we can select data from the users table, okay? Now, just like we grant select options, just like we grant select privileges on a table, we can also grant update, insert, and delete on a table to specific user. In this case, we want to grant update, insert, delete on the users table to app. And once we connect to DB1 with the user app, we can see that the user app can now insert data, update data, and delete data from the users table. If, for example, we decide that the app user should not delete data from the users table, for example, we can revoke this privilege using the revoke command. In this case, we issue revoke delete on users from app. Notice that after revoking the specific permission to delete from the table, the user still has permissions to update, insert, and select, okay? So after we revoke the privileges from the app user, we can see that the app user cannot delete from the users table. If we want to check the privileges that a specific user has on a specific table, we can use the table role table grants from the information schema. Remember, I promised you that we are going to use some of these tables throughout this class. So we fetch from this table the grantee in the privilege type, where the table name is users, the objects that we want to check, and the grantee, the user that we granted the privilege to, in this case, app. And we can see that we have insert, select, and update permissions to the user app on the users table. So if you recall, we also had a schema called restricted, where we wanted to put all the data that all the tables that can potentially contain sensitive information. Now, if we want to grant privileges on a schema, we first need to grant usage on the schema to the user. This is what it looks like. Grant usage on schema with the name of the schema, in this case restricted, to the name of the user, in this case app. Only after we do that, we can start granting permissions on objects in the restricted schema to user app. Now, I want to show you something very cool that I've seen some databases, and I don't know if it exists in other databases, but in Postgres, you can actually grant permissions on specific columns, which I think is wild, okay? So imagine this. Let's say that we have an analyst, okay, that is analyzing the data from some reporting tool, okay? So this user, this analyst, he needs to do, for example, reports to show how many credentials each user has and so on. But this user should not be able to actually fetch the passwords. So I want to grant this user permission to view the data, but I don't want this user to be able to access the passwords. So one way to do that, by the way, is to create a view that only selects the subset of the columns that I want to grant permissions for, and then grant the analyst permissions on the view. But another option is to use permissions on specific field. So in this example, I want to grant up permissions on just the user ID column in the credentials table. And this is what it looks like. Grant select on a list of columns, in this case, just the user ID, on restricted credentials, that's the name of the table, to app, okay? So now, check this out. If I'm connected with the user app and I try to select star from credentials, I get permission denied. If I explicitly try to fetch a column that I don't have permissions on, in the second case, user ID and password, I get permission denied. Only if I fetch only the columns, the specific columns that I'm allowed to fetch, I can see results. So this is extremely useful if you have tables that contain, for example, PIIs. If you need to comply with GDPR, for example, you can actually expose tables to analysts and, data scientists and so on, but you can grant permissions just on the fields that they need to see. So you can grant them options on the user table, but then hide the cell phone number, the national security number, or other pieces of information that may qualify as PIIs, okay? Okay, so far we talked about users, but there's also roles. Roles is a way of grouping permissions okay, and creating a role. The name is actually very intuitive. The main difference between a role and a user in this sense is that a role does not have login privileges by default, okay? So let's create a role. Let's create a role called analyst. We use the create role command and provide a name, in this case, analyst, and we can grant privileges to our analyst role just like we grant permissions to users. So grant select on all tables in schema public to analyst and grant update on users to analyst. So now analyst can query all the tables in schema public and can update the users table. So to grant membership in a role, okay, so let's start with creating a user. Let's call this user Bob, okay? So Bob is an analyst, so I can grant analyst to Bob. And by doing that, Bob now has all the privileges that I granted the analyst role. So if I connect as Bob to DB1, I can see that I can select from users because it's one of the tables in the public schema. So if you issue the command /DU, you can see a list of all the roles in the database. Notice that the analyst role is not a user, so it can't log in by default. We have app and Bob, which we created. You can see that Bob is a member of analyst. And we also have Postgres, which is the super user that comes with every installation of Postgres. And that's it. So you got the basics. There's a lot more, but you got the basics. So we talked about how to create users and roles. We talked about how to grant and revoke privileges from users and roles. And we talked about a very, very cool feature in Postgres that allows you to control privileges at the column level. Truly wild. Okay, so this concludes the second model, and the next model is all about query optimization and indexes. Very, very interesting stuff. Stay tuned and see you in the next video. Hello and welcome to the third and final model in Postgres Essentials. In this model, we are going to talk about query optimizations, and we're going to talk a lot about indexes. We are going to start by describing the path of a query inside the database. We are going to talk about the cost-based optimizer and discuss how the database produces execution plans. We are then going to describe different types of indexes and how we can use these indexes to optimize and improve performance. So let's start with the path of a query. Path of a query is everything that happens when you finish writing your query, click enter. So what happens until you get results back? So let's go through the steps. The first step is the connection step. You have a client application connecting to a server, establishing a connection. So once you hit enter, the first thing that needs to happen is that the text needs to go over to the database. The next step is the parser stage. At this stage, the database takes the actual text of your query and transforms it into a data structure that it can understand, some kind of AST tree. Okay, so for example, if you have syntax error, this is where you fail at the parser stage. The next step, after we have the query represented in a data structure that the database can understand, it goes over to the rewrite system. The rewrite system can make adjustments to the query that don't actually affect the logic of the query. One common example that is carried out by the rewrite system is if you referenced a view in your query, the rewrite system, the rewrite stage would take the view definition and inline it into the query, okay? Now that we have a query that we can understand, we need to stop and talk about the difference between SQL and all other languages, okay? So if you are working with C, Java, Python, Rust, C++, .NET, whatever, you are very used to using controls like if-else, switch case maybe. You're using using things like for loops and while loops to tell the computer exactly what to do at every point. This is called a procedural language. However, SQL is different. You don't actually tell the database how to execute your query. What you're doing is you're using SQL to describe to the database how you want your results to look like. It's then up to the database to figure out what is the best execution plan, what is the best way to retrieve the data to fulfill your query. So this part, the part that takes your query and decides what is the best way to do it, is happening inside the optimizer, the query optimizer or the query planner. This part takes the query and produces an execution plan, okay? The execution plan is something like, use this index to access this information and then access the table. The execution plan can be just scan the entire table. The execution plan decides if we are going to do a hash join, a merge join, or nested loops, okay? So a lot of the magic is happening inside the query optimizer. So once we have an execution plan from the optimizer, it's carried on to the executor, which actually executes the query according to the execution plan and sends the results back to the client over the connection, okay? So let's zoom in on the query optimizer and try to understand how it works. So Postgres uses something called the cost-based optimizer. We are going to talk a little bit about the differences from other types of optimizers, but this is how a cost-based optimizer works in general. So the first thing that the optimizer would do, okay, is to generate all the possible execution plan, okay? So one execution plan might be use the index, another don't use the index, or a third might be use that index or use that index, okay? There's many variations. The more complicated the query, the more possible execution plans you might have. So it starts by generating all the possible execution plans, okay? The next step would be to try and estimate how much each plan is going to cost me. So when we talk about cost, we talk about cost in terms of resources that the database would have to use to fulfill the query. So these resources are memory or CPU, but these resources are mostly I/O, okay? Because doing I/O, actually accessing disk and read data from the disk, is considered to be the most expensive operation. So the more I/O you have, the more expensive the execution plan is going to be and the higher the cost, okay? So after I generated all possible plans and estimated the cost for each one, I simply choose the one with the lowest cost. And the reason is that the lower the cost, the faster the execution is expected to be, okay? So as we discussed, cost is just an arbitrary unit. It doesn't actually mean anything. If you tell me, oh man, you can't believe it, I just executed a query with a cost of 1 million, it doesn't mean anything. Cost is only meaningful when you compare two queries that are supposed, two execution plans that are supposed to fulfill the exact same query, okay? So as we mentioned, cost is affected by CPU, I/O, and other resources, but mostly I/O because that's considered the most expensive operation. So we briefly mentioned that Postgres, as well as most other databases, are using a cost-based optimizer, which is what we saw. We generate all the planes, estimate the cost using statistics, and then we choose the one with the lower cost. There is another type of optimizer called a rule-based optimizer, which uses heuristics, okay? Meaning like if I'm trying to access a table using a column that has an index defined on it, use the index, okay? So most large database engines, the ones that you're probably using, are not using a rule-based optimizer. They're using a cost-based optimizer. However, a rule-based optimizer usually easier to implement. It's much more intuitive. If I had to tell you, hey, build an optimizer, this is most likely what you would do because it's a lot more intuitive. But a cost-based optimizer is proven time and again to be more effective in identifying the best execution plans. So let's look at what an actual execution plan looks like. So if we want to produce an execution plan, if we want to tell the database, hey, I want to execute this query, show me your plan. Okay, we can use the explain command. So we can see explain, select star from sale, okay? And what we get in return is the query plan, okay? This allows us to view the execution plan without actually executing the query. That's important. When we use explain, we go all the way down to the optimizer, but the execution plan is not being carried to the executor. Instead, we get it in return, okay? So let's take a closer look at what an execution plan looks like. So explain, select star from sale. We can see that we have one node and it says scan on sale. Scan on sale means sequential scan on sale, or in other words, the database is planning to scan the entire table, okay? And it makes perfect sense because we asked select star from sale. If, for example, we add a predicate, in this case, where ID equals 1, we can see that now the execution plan is different. This time, the database is planning to use an index scan using cell PK. Cell PK is the primary key, the index that's defined on the ID column, okay? And we can see that the database expects one row in return, okay? Now, let's make it a bit tougher. And this time we say, I select star from sale where ID is less than 100. And we can see that once again, the database decided that it's best to use the index to identify all the rows where ID is less than 100 and then go and fetch from the table. We can see now that the database expects a bit more rows. In this case, the database expects 113 rows in return. This is not an accurate number. This is just an estimate, okay? Now, finally, let's select star from sale where ID is less than 100,000. And this time, and that's interesting, we can see that the database decided not to use the index. Instead, it decided to just scan the entire table, okay? This is a very interesting observation. It means that the optimizer actually looks at the values that we use in our query to try and determine the best execution plan, okay? The database is doing that using various statistics that it collects on our data. This is a little bit outside the scope of this class, but it's a very, very interesting topic to explore. So far, we've used explain to produce the execution plan, but sometimes it's useful to both produce the execution plan, but actually execute the query. For that, we can use explain with analyze and timing on. You can see the highlighted row. What this will do is several things. First of all, it will execute the query and return the execution plan, unlike explain that only returns the execution plan. Explain analyze will also execute the query and return the plan. In the output, we can see that we have two timings. First, we get how long it took the optimizer to come up with the plan. In this case, it was 1/10 of a millisecond. And we can also see how long it took the executor to execute the query. In this case, 15 milliseconds, okay? So this is very useful. Sometimes you want to benchmark a query, do some back and forth to see how different things affect your query. So using explain analyze is very useful for that. In addition to the timings, you can also see the number of rows that Postgres expected, in this case, 100,000. And in the second row, you can see the actual, which is how many rows were actually returned by this node, processed by this node. In this case, Postgres expected 100,000 and received exactly 100,000. So this means that the estimate was spot on, okay? But once again, this is a bit outside the scope of this class, but it's a very interesting topic. So now that we know how to produce execution plans, in the next couple of videos, we are going to see different types of indexes, and we are going to see a lot of execution plans. So stay tuned. Hi, hello. In this video, we are going to talk about B-tree index. That's the king of all indexes. If you're using Postgres and you're not sure what you're using a B-tree index. So B-tree index is the default and most popular type of index and most likely what you need, okay? It's used to enforce unique constraints and primary key constraints. We saw that when we talked about data integrity, and it has many features which we are going to see in this video. So let's start by understanding how a B-tree index works. So if we have the values 1 through 9 and we want to create a B-tree index, we start by, if you notice the leaf blocks at the bottom, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then on top of them, we have the root block, which acts like a directory to all the other leaf blocks. Let's see how it works. Let's take the index we just built and try to search for the value 5. So we start from the root block, okay? So every value left of 3 are values smaller than 3. So we're looking for the value 5, so we can exclude this leaf block. Next, we look for the next entry in the root block, which is 7. So the pointer between 3 and 7 is a pointer to the leaf block that holds all the values between 3 and 7. The value that we are looking for is 5, which is between 3 and 7. So I follow the pointer to the leaf block and start scanning the leaf block. I go from left to right. In this case, I start with 4. It's not what I'm looking for. I found the value 5, I have a match, and now I can follow the pointer to the row in the table. Okay, this is how a B-tree index works. Now, in order to understand how B-tree works and the different types of B-tree indexes, I want to do an actual use case. So let's take an imaginary URL shortener system. If you're not sure what it is, then a URL shortener system is basically a system that provides short URL that can redirect to very long URLs. Why is this useful? 2 reasons. First one, using the short URL, every time we redirect, we maintain a counter, and this is very useful for analytics. So if, for example, you have this campaign and you want to know how many people clicked your link, you can use a short URL, and it will keep track on how many times people click that link. Another common use case for URL shorteners is when you want to, for example, share a very large URL or send in an SMS, but these environments are constrained. SMS is restricted to a certain number of characters, and tweets are constrained to a certain number of characters. So a short URL can provide you with a smaller URL for a very short URL. So we are going to actually build a table for a URL shortener. So let's start. We start by creating a table called short URL. We have an ID column which is an integer generated by default as identity, and that's our primary key. We have a key, which is the short random part of our short URL. And notice that it's length 6, short, it's unique, and it's not null. Okay, so we have to provide a key for every short URL. We have our actual URL that we want to redirect to. It's unrestricted text and it's required, not null. We have hits, which is how many times we redirected the short URL to the long URL. This is our counter, and it's type integer, and it's also required. And we have created at, which is a timestamp that indicates when was the short URL created. At the end, you can see that we added a constraint to make sure that the hits cannot be negative, okay? It doesn't make sense for hits to be negative, so they need to be greater than or equal to 0. Now, for the sake of, experimentation, we added 10,000 short URLs to the table. This is what it looks like. You can see the ID. It's just a sequential ID populated off a sequence. Then we have the key 6 digits that appear in the short URL. And then we have the long URL, which is randomly generated in this case, but this is the long URL we want to redirect to. We then have the hit counter. We can see that URL number 2 was hit 7,637 times, and it was created on the 1st of January 2021, okay? So now we are going to do several use cases on this table and trying to optimize them. So the first business question that we want to answer is, we want to find all the unused short URLs, okay? We want to find short URLs with no hits. So if we just go about and write this query, we issue explain analyze because we want to execute the query, get the timing, and view the execution plan. So we issue explain analyze select star from short URL where hits equals 0. If you look at the execution plan, you can see that it took 2 milliseconds and Postgres decided to use a sequential scan on the short URL table. So basically, Postgres scanned the entire table. Now at this point, anybody with a bit of experience with databases would say, hey, that's a very long time. Let's create an index. So let's create an index, okay? Let's create a B-tree index on the hits column because this is what we are filtering by, right? So create index short URL hits IX on short URL using B-tree hits, okay? So now we have a B-tree index on the hits column, okay? The B-tree part, using B-tree part at the end, is the default. So starting from now, we're not going to say using B-tree. We're just going to write short URL hits, okay? So now let's try the query again, okay? Explain, analyze, select star from short URL where hits equals 0. This time, we can see that Postgres used our index on the hits column to do a bitmap index scan, and then use the results of this bitmap index scan to access the table. This is the part that says bitmap hip scan, okay? You can see the hip blocks 61, which means that Postgres ended up reading 61 blocks from the table using our index. We can also see that the timing is lower. Previously it took 2 milliseconds, but now it only takes 0.2 of a millisecond to execute the query using our index, okay? So 99 of the people would stop here and say, that's a huge improvement. I can call it a day. Let's go for lunch. We're done. But you took the time to take a Postgres class, so you can do better. Let's ask ourselves, how many actual unused short URLs we actually have, okay? Let's count them. So select count from short URL where hits equals 0. So we only have 98 short URLs which are unused, okay? Which, if you think about it, kind of makes sense even from a business perspective, because once you create a short URL, you immediately try it. So, most short URLs should have at least one hit. So we found 98 with 0 hits. So that's less than 1% of the table, or in other words, that's a very small portion of the table. Now, if you go back to our index, you say, wait, so we have an index that includes all the rows in the table, all the 100% of rows in the table. But we only care about a very small portion. We just saw that we only care about these 98 rows, okay? And we don't expect that, that ratio to be significantly larger in the future. So what if we could just index the portion of the table that we actually care about? So lucky for you, we can. Let's see what it looks like. So first of all, this is called a partial index, okay? We can index only a portion of the table, hence partial index. Let's see what it looks like. This time we create an index. We call it short URL unused part IX. I like to call partial indexes part IX to make sure that I realize they are partial. So we use on short URL, that's the name of the table, and we index the ID column, but, and that's the addition, we can add a where clause where hits equal 0. this will index the short URLs, the IDs of the short URLs, only for short URLs where the hits equals 0, okay? So let's try our query again, okay? Explain and analyze select star from short URL where hits equals 0. And that's the exact same query as before. But look at that. Now the database decided to use an index scan on our unused partial index, okay? So that's amazing. And you can see that the timing is still very, very low, okay? So at this point you ask, okay, you're the man. You just did the exact same thing. So what's the point? Let's look at the size of the indexes. So our previous index, which indexed all the rows in the table, okay, was 240K kilobytes. But the partial index that only indexes the part that we actually need, the part that we care about, is just 16 kilobytes. Now, if you ever worked on a very large database, you know that B-tree indexes can be very, very big. If you have tables with billions of rows, even millions of rows, you'll start noticing that the indexes become so big, okay? So here, we only have 10,000 rows. That's nothing. But if you have millions of rows, this can end up a difference of gigabytes on gigabytes. So before I go into the recap on partial indexes, you can actually read this article I've written at the bottom where I share how we freed up 20 gigabytes of unused index space simply by using and utilizing partial indexes. So partial indexes, as we've seen, can produce much smaller indexes simply by the fact that they index less rows, right? Just the portion of the table that we actually need. The downside of partial indexes is that they can only be used by queries that use the exact same predicate as the one we used. So if you have a query that's using hits equals 0, Postgres will consider the index for that query. But if you have a different type of predicate, Postgres is not smart enough to use the index, okay? Even if you think that it might, it's not. You need to have the exact same predicate. I personally found that nullable columns are a great candidate for partial indexes because usually when you have an index on a partial index, on a nullable column, a column that can accept null values, usually you would not have a lot of queries that would search for null values. You might have. It's not impossible. It's not unreasonable. But I found that usually you won't do that, in which case you can exclude the null values from the index, making it very, very small. This is actually what we've done to save the 20 gigabytes. So I'm a big fan of partial indexes, and I think that you should use them whenever possible. So let's consider another use case. Okay, now we want to resolve a key to the full URL. So resolve a key meaning that someone clicked our short URL, and we now have the short random part at the end, and we need to figure out which long URL we need to redirect to. So this is one of the most common queries that a URL shortener executes, and it needs to be very, very fast, okay? This is like the bread and butter of the URL shortener. So this is what the query looks like. Select URL from short URL where key equals something. In this case, key 123, okay? So let's inspect the execution plan. Let's do explain, analyze on that query, and we can see that the database is using our using the index short URL key, which is the index, the unique B-tree index used to enforce the unique constraint on the key column, okay? So the plan here is basically use the index to find the matching row and then go to the table, read this row, and give me the URL, okay? Now, if we think about the scenario, we know that we have a query that is executed a lot. We said that this is what the short URL does. It redirects. This is what it's doing. It's getting short URL, and it needs to resolve it into a long URL. So it's doing it constantly, and it's very important that we be very, very fast. Now, so we have this query that executes lots of time, and but we only actually need the URL, right? So we need the URL by the key. We query for the key, but we then go to the table and we only get the URL. So what if we could just add the URL right there in the leaf block of the index, right? That's wild. Imagine that. So that's actually possible, and it's called inclusive index. You can actually store additional data in the leaf block of the index. So let's see what it looks like. We're creating a unique constraint called short URL key, including URL, okay? This is my convention. I like to make sure that I know exactly which columns are included in the index. So short URL key, including URL IX on the table short URL, we're indexing the key, okay? We're indexing the key column, okay? This is the column that we fetch by. And then we say include URL, okay? So this tells Postgres, create an index on the key column, but then in the leaf block right next to the key, put the URL. Put the URL from the table. Now, if we execute the query again, the exact same query using explain analyze, we can see that this time Postgres was able to use what's called an index-only scan. In other words, Postgres was able to fulfill our query just from the index. It didn't even need to access the table. So previously, it used the index to find the row and then access the table to get the URL from the row. But this time, the row was already in the index. So Postgres did not need to access the table as well. This is exactly what inclusive indexes achieve. So inclusive indexes allows the database to, under some circumstances, of course, to fulfill queries without accessing the table, just by accessing the index. The downside is that the index could get very, very, very big. Imagine that URL is a very big value, key is a piece of text, and you store both of them 2 times, once in the table, once in the index. Index can get very, very big. So inclusive indexes should be used with caution, because accessing the table is not as bad as it sounds, okay? But it's an option. If you have a very, very wide table, okay, and you have a bunch of these queries that access a very limited set of values from the table, you can consider inclusive indexes. I personally found that a good candidate for inclusive index would be non-unique composite indexes, okay? I'm going to come back to that at the end. Let's look at another use case. This time, we want to find all the URLs by domain, right? We want to find out how many short URLs we have pointing to akibenita.com. So for that, we can use this query using this regular expression, select star from short URL, where, and this substring basically extracts the domain part from the URL. And we can see that we have 3 URLs that are pointing to the domain akibenita.com. Okay, that's nice. Now, if we look at the execution plan, we can see that the database is doing a sequential scan, meaning the database is going to scan the entire table. And we can also see that we've had full table scans in the past, but this time it takes a lot of time, okay? It takes 40 milliseconds, almost 50 milliseconds to complete this query. And the reason for that is that for every row, Postgres needs to apply this regular expression and check the condition. So this can be very CPU intensive. This is why it takes so long, okay? It's not just sifting through the data. You actually need to apply this regular expression, evaluate this expression, check if it's true. So we have this query, and it's very useful. There's a strong business need for this query, but every time we query this table, we basically recalculate the entire expression for every value every time. This sounds a bit wasteful. So what if, and as you can guess, it's possible. What if we could just index the result of this expression, this specific expression? So this is called function-based index, which happens to be the database object with the coolest acronym, FBI, okay? So function-based index allows us to index the result of an expression. In our case, we want to create an index on the domain part of the URL. So we can use, check this out, create index, short URL domain IX on short URL, and then we provide the expression we want to index. So this index is the substring from this URL shortener. So basically, if you look at the URL below, you can see that what this regular expression is doing is extracting the part highlighted in yellow, the domain part, and indexing this part, okay? Now, if we try the query again, display analyze, select star from where substring, and notice that I'm using the exact same expression, we can see that this time the database is using our index to do a bitmap index scan, and then is using the result of this bitmap to do a bitmap heap scan on the table, okay? And if you look at the timing, it's so much faster. Before it was 50 milliseconds, and now it's less than 1, okay? So that's a huge improvement. And this is thanks to the fact that we didn't have to reevaluate this expression for every row because the result was already stored in the index. Now, one thing you really need to be careful with function-based indexes is that you need to use the exact same expression, okay? If you look at the top query, I'm using the exact same expression, and the query is very fast because the database was able to use the index. However, if you look at the second query where the regular expression is slightly different, I added this HTTPS at the beginning, you can see that the timing is back to 15 milliseconds, meaning that the index was not used. And the reason for that is that the expression is different, okay? So using a function-based index, the index can only be used if you use the exact same expression. And I personally, and I have to be honest here, I'm not a big fan of function-based indexes because I find that if you have the ability to make changes to the application, it's usually a better solution to just use another column. Like you can add a column for the domain and just calculate the domain once when you insert the row, and then use a regular index on that if you need. However, there are situations where, for example, you have a third-party or closed source application using a database that you operate, and you don't have any ability to change the code in this application, and you identify that this application is using a very specific expression and is unable to utilize any index. A function-based index can help to compensate in this case, okay? So, take function-based indexes with a grain of salt. Finally, we have composite indexes. I don't have any use case here that makes sense, but I just wanted to include them because you should know that B-tree indexes can be used for indexing multiple columns, okay? So in this case, we have an index on both the URL and the key. Doesn't make much sense, but you can do that. This is what the syntax looked like. So composite index is mostly makes sense when you have columns that are queried very often together. I personally found that composite indexes are normally useful when you need to enforce a unique constraint. So normally you would see a unique composite constraint, in which case the constraint, the index is used to enforce a unique constraint and not just for performance purposes. Composite indexes is not always better than having individual indexes. If you have individual indexes, for example, if you have an index on URL and key, they won't necessarily perform worse than an index on both of them together, okay? So once again, if you need composite indexes, just use composite indexes. I would say though that the order of the fields in a composite indexes is significant, even if you're using them for unique to enforce a unique constraint. So usually you want to put the frequently filtered by columns first. So if you have in the composite index, you have an index that you are using to filter by a lot, put it first, okay? And the second thing you need to consider when choosing the order of the fields is that you want to have fields with more distinct values first, okay? So the more distinct values the column has, you want to put it first, okay? So just a few things to consider about the composite index. Now, that's a fun slide. You can actually mix and match everything that we've talked about. So if you want to get a very a wild example, then here we have a partial function-based inclusive index, okay? We have an index that is indexing the domain part of all the unused shows URLs, and we include the URL in the leaf block, okay? So that's a partial function-based inclusive index. So you can mix and match, okay? That's fun. So before we finish, I want to discuss something that I think can sometimes be very confusing, and that's nulls. We talked about null values. Null values indicate missing values, and different databases treat or index null values differently, okay? So some database like Oracle, for example, when you create an index on a nullable field, the null values are not indexed by default, okay? So theoretically, if you have an index on a column that all the values are null, the index should be very small because it's not indexing anything. But in Postgres, however, null values are indexed, okay? So the same example for Postgres, you would have a full-sized index on these null values. So this is one thing. Another thing is that in how Postgres handles unique constraints on nullable columns, okay? So consider this example. We have table T with column N. So this column N is a number and it's nullable, okay? So we create a unique index on N because we want N to be unique. So we insert the value null into the table. So now we have one row in the table where N is null, okay? And now we insert another null into the table. And remember, we have a unique constraint. So what should happen? Okay, take a second, think what should happen. So we already have a null in the table, and now we're trying to add another null. We have a unique constraint in place because we don't want duplicates in the table. So what should happen? So before Postgres 15, this would pass because in SQL, null does not equal null, okay? So in terms of uniqueness, there is no violation here. So even if you have, prior to Postgres 15, if you have a unique index on a nullable column, you need to expect multiple rows with the value null, potentially with the value null, okay? So starting at Postgres 15, there's a new option to define how nulls should be treated. So if we want to disallow multiple null values, or if we want to treat null values as equal, okay, we can add the option to the unique index. We can add the option nulls not distinct, okay? And if we do that, when we try to add the second null, we are going to get a unique constraint violation, okay? So this is something that's new in Postgres 15. So you need to be aware of that if you're using unique constraint, unique index on a nullable column. So recap of B-tree indexes. So B-tree is the default type of index in what you normally need. If you're not sure what you're using a B-tree index. A B-tree index is used to enforce unique constraint, which is also used to enforce a primary constraint. And there's many features. We saw partial indexes, we saw FBI function-based indexes, inclusive composite, lots of fun. So this is it for B-tree index. Okay, so while B-tree is the most popular, there are additional types of indexes in Postgres that can be more beneficial. And this is what we are going to do in the next 2 videos, okay? So stay tuned. Hi, in this video, I want to talk about hash indexes, which I like to call the ugly ducklings of index types in Postgres. Hopefully by the end of the video, you'll understand why. So before we talk about hash indexes, let's talk about performance and what's it all about. When people want to say, I want this to be more performant, what exactly do they mean? So I say that when they say something needs to be more performant, it basically means that they need to balance their resources in a better way, okay? So we have many different types of resources. We have CPU, we have memory, we have disk space, we have cost. And each type of resource is more significant at different times, depending on the system, right? It's not just speed. And let's take an example, okay? Let's say that we have this batch processing that runs at night. So this batch processing currently runs in 1 minute, and it takes up 1 gigabyte of disk space, which costs us lots of money, okay? So if you had to optimize this process, and you were able to make the process run in 2 minutes instead of 1, but then it would not consume any additional disk space at all, would you do it? In this case, I believe that most people would, because it's a nightly batch job. Who cares if it takes 2 minutes, right? However, if you have something that executes in the middle of the day, you might want to make it more quick, or you might want to make it less CPU intensive while the app is running, while the application is running. So the resources change depending on the use case, okay? So one of the things I want to start looking at when we talk about performance in this videos and the next, so far we've looked at speed, but now I want to add another dimension. I want to start talk about the size of the objects that we create, the size of the table, the size of the indexes. So to get a size of the table, we can use the function pgTable size, and we can make it look nice using the function pgSize pretty, or we can use /dt plus with the name of the object and get the size. You can see at the bottom right, 832 kilobytes, okay? If we want to check the size of an index, we can use a /di plus command with the name of the index, or we can use a wildcard. In this case, I've used a very specific naming convention, so I can do that. I can do /di plus short URL star, and it gives me the 2 indexes, the primary key and the unique index that I have defined on the key column, okay? So with that in mind, let's start another scenario on our URL shortener table, okay? This time, we want to do a reverse lookup. So a normal lookup is where we find the key. We look for the key and get the URL. This time, we want to do a reverse lookup. We want to search for all the keys that point to a specific URL. This is what the query looks like. Select star from short URL where URL equals something, okay? So just quick reminder about the URL. The URL is not unique. You can have multiple short URLs pointing to the same URL. However, it is almost unique. If you actually look at the data and if you exercise some common sense, you'll find that it doesn't make a lot of sense to have a lot of short URLs pointing to the same URL. So naturally, it will most likely be almost unique, okay? So it's not unique by definition, but it will have a lot of distinct values, okay? In addition to that, a URL by nature can be a very large piece of text. If you think about the amount of, large domain names and then paths and then you have query prompts. Sometimes you have actually data encoded into the URL. So URLs can be very, very big. So it can be a large chunk of text. So now let's start our optimization with the most naive approach. Let's just execute the query and see how long it takes with no indexes. So we do explain analyze select star from short URL where URL equals this URL. And we can see that Postgres did a full table scan, which makes perfect sense because there is no index. And it took 15 milliseconds, okay? So now, like 99% of the people would say, okay, we want to optimize that, so let's just add a B-tree index on it, right? Let's slap a B-tree index on the problem. So let's slap a B-tree index on the problem, and let's do create index short URL IX on short URL. We created an index. We execute the query again, and we can see that the B-tree index is used, and the execution time is reduced significantly, right? So the full table scan was 15 milliseconds for the reverse lookup, and using the B-tree index on the URL column, we were able to get this down to less than almost 1/10 of a millisecond, okay? That's pretty grand, right? I know it's great, but bear with me. Let's take a short break and see how a hash index works in Postgres. And we're going to do that by building a hash index together. So let's say we have these values A, B, C, and D, okay? So the first thing that we want to do is we want to apply a hash function on these values. So Postgres has lots of hash functions for different types. In our case, this is a text. So we use hash char, or this is a character specifically. So we use hash char. So now that we apply the hash function on each of our values, we get the result. We get the hash value, right? So now we divide our hash index into two buckets, okay? So this is not something that you decide how many buckets. This is something that Postgres decide. It's determined by looking at the LSB. But let's say that we now want to divide our hash index into two buckets. So we take each of the hash values and we apply modulo 2 on them. So we can see that the value A goes to bucket 1 and B, C, and D go to bucket 0. So now we can build our index, okay? So this is our index. In bucket 0, we have 3 hash values, each pointing to the row, okay? The row in the table that contains this value. And we have bucket 1 with 1 hash value pointing to 1 row. Now let's use our hash index to search for the value B. So we take a similar process. We apply the hash function on the value B and get the hash value. Then we apply modulo the number of buckets, in our case 2, and we find that this hash value may be in bucket 0. And then we search for the hash in bucket 0, and we find a matching hash value, and we find the pointer to the row, which is row number 2. This is how a hash index works, okay? There's a lot of implementation details, but basically this is how a hash index works. So now let's try to create a hash index for our reverse lookup scenario. So to create a hash index, we do create index. I like to call them HIX, okay, to mark them as hash indexes on short URL. And this time, it's not the default B tree. We want to use a hash index, so we do using hash on URL, okay? And after we created the index, we execute the query again. That's the exact same query, okay? And look at that. First of all, Postgres decided to use the hash index, okay? So we have index scan on short URL HIX. That's the hash index we just created. But, and that's one of the points here. Look at the execution time. Okay, let me show you the table. look at the execution time. So a B-tree index was 0.1. A hash index was 0.06. Okay? So a hash index was actually faster in this case than a B-tree index. But you know what? That's not all. Okay? Remember, the hash index was faster, but look at the size of the index. So the B-tree index in this case was 4.5 megabytes, but the hash index was only 4.1 megabytes, okay? So the hash index is not only faster, it's also smaller in size, okay? That's magic. So I want to show you this chart. What I did here is I inserted a lot of rows into the table. And as I was inserting the rows into the table, I measured the size of the indexes. So I had a hash index on the URL, like we just created. And I also created a hash index on the key. The key is a very small text compared to the URL. I did the same with B-tree. So I had a B-tree on the URL and I had a B-tree on the key. And take a look at what we see here, okay? On the bottom axis is the number of rows and the left axis is the size. So if you look at the red line, you'll see that the B-tree on the URL, that's the B-tree on the URL, as we insert more rows into the table, the size of the B-tree of the URL becomes very, very big. You can also see that compared to the green line, which is the B-tree on the key column, which is the smaller piece of text, the B-tree on the key grows, but it grows in a slower pace than the B-tree on the URL. So the first observation here that you need to understand is that if you remember, when we talked about the B-tree index, we saw that the value that we indexed is stored in the leaf block, okay? So when the value is big, it affects the size of the index, right? So in this case, we index the same number, the same amount of rows, but because the URL is a big text and the key is small, the size of the B-tree on the URL is significantly larger than the size of the B-tree on the key. Or in other words, a B-tree index, the size of the B-tree index is affected by the size of the values it indexes, okay? Now let's take a look at the sizes of the hash indexes. These are the yellow and red and blue lines at the bottom. So first of all, you can see that the hash index is constantly smaller for both the key and the URL. So in this case, in our particular scenario, a hash index is almost always smaller than the corresponding B-tree index, okay? The second observation that we can take from this chart is that the hash on the URL and the hash on the key, okay, grow exactly the same way. Or, in other words, it seems like the hash index is not affected by the size of the values it indexes. And the reason for that is that the hash index does not store the values in the index. Instead, it stores the hash values in the index, okay? This is why it's not affected by the size of the index, of the values it indexes, okay? Now, those bumps that you see in the hash index, these are bucket splits. So once the buckets get filled up, Postgres does some maintenance on the index and splits some of the buckets to make room for more. So this is also a nice observation about hash indexes and the way it behaves, because a B-tree seems like it grows linearly, but the hash index grows in steps. So the way this hash index works comes with its own restrictions. So first of all, because hash index does not contain doesn't contain the indexed values, you can't use a hash index to enforce a unique constraint, okay? The second restriction on hash index is that you can't have a hash index on multiple columns. You can't have a composite hash index. Also, because a hash index is not actually storing the values in the index, you can't use a hash index for sorting, and you can't use a hash index for range searches. So a hash index is mostly useful when you have queries that look for specific values, that use comparison, okay? So let's do a quick recap on hash indexes. So hash indexes are ideal when you have a lot of distinct values. If you have a lot of duplicates in the table, then a lot of the hash values would map to the same bucket, and the hash index would not be as beneficial. Some of the values that I found to be ideal candidates for hash index are actual hashes, because they are very big, okay, and usually very unique. Also, UUIDs are very, very good candidate for hash index. So if you have a UUID that you don't need to enforce a unique constraint on, consider a hash value, consider a hash index. Also, as we saw, a hash index is not affected by the size of the values it indexes, because it stores hash values and not the actual values. We also saw that a hash index can be both smaller and faster than a B-tree index. We actually saw that. I did not make this up. Now, the reason I call hash index the Ackling Duckling index types in Postgres is that hash index goes way back. However, before Postgres 10, it was discouraged. If you open the documentation for Postgres 9, I think, you get this huge warning saying this is not production ready, do not use a hash index. So because of that, a lot of people got used to not using hash indexes in Postgres. But starting at Postgres 10, it actually became production ready, and it's very, very useful. So people are gradually starting to get familiar with additional types of indexes in Postgres, mostly hash index. So, I think it's a good trend. So we talked about B-tree, we talked about hash. In the next video, we are going to talk about block range index, or BRIN. So stay tuned. Hi, in this video, we are going to talk about block range index, or BRIN, okay? So our scenario on our URL shortener for this type of index is a range search, okay? We want to find all the short URLs that were created in a specific date range. In this example, we want to find all the short URLs that were created in February 2021, okay? Okay, so first of all, we start our investigation by establishing a baseline. So we execute the query using explain analyze with no indexes, and the database does a sequential scan, a full table scan on the table, and it takes 19 milliseconds, okay? The next step, we try to optimize. So naturally, we go for a B-tree index, and we create a B-tree index on the created date, and we issue explain analyze with the exact same query, and we can see that Postgres decided to use our index. You can see an index scan using created at IX, and the execution time is now much lower, okay? So the full table scan was 19 milliseconds. The B-tree index scan took only 2 milliseconds. Now, after discussing hash index before, we now added another dimension to our metrics, and we now look at the size of the index. So for a full table scan, there's no index, size is 0. And the B-tree index on our date column was 2.2 megabytes, okay? So just like before, I think 99% of the people would stop here and say, let's go for lunch, it's good. 2 megabytes, it's not a lot. 2 milliseconds, it's fast enough. It's within our performance budget. No problem. Let's go. Stop digging into it. But I want to take this opportunity and introduce to you another type of index, which I personally find very exciting, okay? So let's see how a BRIN index works. BRIN stands for Block Range Index, okay? So let's imagine we have these values, each one in a single page, okay? Because block range index talks about pages. We can have multiple rows in a single page, but for the sake of discussion, let's imagine that we have exactly one row in each page, and these are the values that we're indexing. So we have 1 through 9. The next step in the block range index is to divide the range into ranges of adjacent pages. Adjacent pages are pages that are next to each other. So basically, I just took 3 adjacent pages and grouped them together. You see, 1, 2, 3, that's one group, 4, 5, 6, second group, 7, 8, 9, that's the third group. I grouped them into a group of 3 adjacent pages. The next step, and yes, it's that simple, we just keep the range for each group, okay? So 1 through 3 is 1 through 3, right? 4, 5, 6, 4 through 6, 7, 8, 9, 7 through 9, okay? And this is our BRIN index. Now let's use our BRIN index to search for the value 5. So we go for the first group, first range, and we say, is 5 between 1 and 3? The answer is no. So we know that 5 is definitely not inside this range, okay? We then go to the second range and we ask, is 5 between 4 and 6? In this case, we don't say that 5 is in this range. We say that 5 might be in this range. We don't know that for a fact. It might not be in this range, but if it is, it is. If it does exist in the table, it might be in this range, okay? So the last range is 7 through 9, and we say that 5 is definitely not here because 5 is not between 7 and 9. So now using the BRIN index, we know that we only need to scan blocks 4, 5, and 6. So basically using the BRIN index, we were able to eliminate 2/3 of the table. We can now focus only on blocks 4, 5, and 6. So let's create a BRIN index on our created at date, okay? Create index. Short URL created at IX on short URL using BRIN, okay? This is not a standard index type, so we need to provide using BRIN created at. And then we execute the query and we can see that the database decided to use our BRIN index. You can see bitmap index scan on short URL created at BIX, and that's the index we created. Now, if we look at the timing alone, the timing is slightly higher than before, okay? But let's look at the size, okay? So I issue /di plus with the prefix of both indexes. And as you can see, the BRIN index is very, very small compared to the B tree. So the B tree is more than 2 megabytes, while the BRIN is just 48K. Okay, that's very, very small. So if I put BRIN and B-tree and the full table scan, what I can see here is that while B-tree is the fastest, BRIN is the smallest. But BRIN index is significantly smaller than a B-tree index, but the timing difference is not that significant. So basically, if I'm willing to pay the additional 3 milliseconds between 2 and 5 milliseconds, I'm able to save more than 2 megabytes of disk space on the B-tree index. Okay? So this is where we need to decide on the trade-off. Previously, on the hash index, it was an easy decision because it was faster and smaller. But this time, we can see that it's much smaller, the BRIN. It's much smaller, but it's only slightly slower, okay? Smaller, but slightly slower, okay? So now let's try to understand BRIN limitations, okay? So Previously, we assumed that we had perfect correlation. We assumed that the data is organized on the disk, is sorted nicely on disk. Right, it was 1, 2, 3, 4, 5, 6, 7, 8. So all the adjacent pages were lined up very neatly. But what if we assume for a second that our pages are not organized nicely like that? Let's take, once again, the same numbers, but this time they are sorted in a different way. So now we do the exact same thing. We take groups of three adjacent pages, and we create our BRIN index. You can see 2 through 9, 1 through 7, 3 through 8. And then once again, we try to search for the value 5. So now 5 is between 2 and 9, 5 is between 1 and 7, and 5 is between 3 and 8. So in this case, using the index, I was unable to eliminate any part of the table. I need to scan everything. So in this case of poor correlation, the BRIN index is completely useless, okay? Now let's look at another aspect. Let's say that we now back again with perfect correlation. We have 1 through 9 neatly sorted. But this time, instead of indexing ranges of 3 adjacent pages, I'm going to index ranges of 5 adjacent pages, okay? So I want to have 5 pages per range. So I do the exact same thing, but this time instead of taking groups of 3, I'm taking groups of 5. So if you look at that, the index is smaller. I only have 2 entries in the index, right? Previously, I had 3 entries in the index. Now I have just 2 entries in the index. And if I use this index to try and find the value 5, okay, so I know it might be in the first range, but definitely not in the second range. So now, using the index, I was able to narrow my search just to blocks 1, 2, 3, 4, and 5, okay? So I have a smaller index, but I was able to narrow the search to 5 blocks instead of 3, like what I had before. Let's go to the other extreme, and this time, let's say that I want to have just 2 pages per range, okay? So this is what my index looks like, and I'm searching for the value 5, okay? So this time I have 5 entries in my index, so my index is bigger, but it's much more accurate because now I'm able to reduce my search just to blocks 5 and 6. So when I had 3 pages per range, I ended up searching 3 blocks. When I had 5 pages per range, I needed to search 5 blocks. But now with 2 pages per range, I have a bigger index, slightly bigger index, 5 entries, but I only need to search 2 blocks, two blocks, right? So to set the number, the pages per range for a BRIN index, you can provide, using BRIN, create a that with, and then inside parentheses, you can provide the number of pages per range, okay? So the lower the pages per range, the more accurate the index, but the bigger it is, right? Because I have more ranges, so the index is bigger, but it's more accurate, okay? The higher the pages per range, the smaller the index, I have less entries, and the less accurate it gets, okay? So the default is 128 and the minimum is 2. I usually recommend to start very small and gradually increase, okay? So the BRIN index has different types of operators. The operator that we presented in this video is the min-max, because for each range, it keeps just the min and the max values. And it's useful when you have data with high correlation, okay? But there are additional operator classes that you can use. For example, you can use, starting Postgres 14, you have the min-max multi. This is a type of operator that instead of keeping just one, just keeping the minimum and the maximum for each range, you keep multiple ranges, multiple min and max values for each range. This is ideal when you have high correlation data with outliers, okay? And also you have a Bloom filter that you can use, a Bloom operator, that for each range, you can create a Bloom filter. And this actually makes BRIN index useful for data with low correlation. So a quick recap about BRIN indexes. BRIN indexes are ideal when the data is naturally sorted on disks. There are different types of data that are naturally incrementing. Like if you have an append-only table and you have a column to keep track of when the row was created, then this row would be gradually incrementing. So on the disk, as you scan the table, the value would be slowly increasing. You can actually find these columns using the value in the dictionary table PG stats in your information schema. There's a column called correlation, and you can use that to identify columns with high correlation, which can be good candidates for a BRIN index. Also, BRIN index is usually ideal for tables that don't update frequently, because when new rows are added to the table, the index is not updated immediately. The BRIN index is only updated when the table is vacuumed. So generally speaking, I would say that BRIN index is good for analytics environments, data warehouses, stuff like that. For OLTP systems, BRIN can be a bit tricky, okay? So finally, we talked about pages per inch and how to adjust the value to control the size and the accuracy. Remember, the main advantage of a BRIN index is that you can use it to satisfy queries in a reasonable amount of time with a very, very small size of index, okay? So if you have like a data warehouse system and you have lots of ad hoc queries and it's very hard to predict what people are going to use, then these columns that can benefit from BRIN index, you can throw an index on them, and it will be very small, so it would be very resource light, I would say, and it would make queries faster, okay? So we talked about B-tree, we talked about hash, we now talked about BRIN. In the next video, we are going to talk about index maintenance and best practices. Extremely important, so stay tuned. That's the last video of this class. Okay, this is our last video of this model and this class. Now that we know about the optimizer, we know about B-tree, about hash, and about BRIN, it's time to talk about index maintenance and some best practices, and I would say even common misconceptions about indexes. So let's start. The first misconception that I want to talk about and bring up is that indexes are not always the best way to execute a query. There's a certain misconception that once you have an index, if the database decided not to use the index, the database must be wrong. So let's see an example. Let's create a table called haystack, okay? And into our haystack, we are going to insert one needle and 999 hays, okay? Now we create an index on our haystack, okay? And we try to find the needle. So, and I hope you appreciate my commitment to this metaphor, but we are looking for the needle in the haystack, okay? So if we do an explain select star from haystack where what equals needle, we can see that the database decided to use our index on the haystack. So the index is used. However, if on the same haystack we're trying to look for hay, okay, we can see that the index was not used. The database decided to just go on and scan the entire table, okay? So what this means is that When the database thinks that it's going to scan a large portion of the table, a full table scan might be better. If you think about our haystack scenario, would you really go through the index to read 99,999 hays? Probably not, because then you would have to read both the index and the table. Also, when you're doing a full table scan, the database is able to utilize certain, apply certain optimizations on the I/O that it's not possible when you're doing the scan through the index using random I/O, okay? So if right now you're thinking, so Aki, just give me the magic number, like more than 50%, more than 30%, more than 10%. The truth is that there is no magic number. It really depends on the type of data you have in the table, the type of indexes you have, and many, many other factors. But you do need to think about that if you apply the condition and the database decided to use a full table scan, while there is an index, there might be a good reason for that. The next misconception I want to burst is that indexes are not free, okay? As we've seen many times throughout these the previous videos, indexes can consume a lot of disk space. I personally have indexes that weigh more than the table, okay? And also, indexes slow down insert, update, and delete operations, okay? But don't take my word for it. Let's actually do an experiment. Let's create a table with 5 columns, okay? We call the table T, and we have A, B, C, D, E, all floats. Now we want to insert 100,000 rows into this table, and we can see that it took 118 milliseconds, okay? That's great. Now let's do the exact same thing. We drop the table, recreate the table, okay? But this time, before we insert data into the table, we are going to add 5 indexes. We're going to add a B-tree index on every column in this table. So we have a total of 5 indexes. Now we do the exact same thing. We populate the table with 100,000 rows, and check this out. Almost 900 milliseconds. That's 7 times slower than adding the data without the indexes. So this slowdown can only be attributed to the addition of the indexes, okay? So remember, when you are making changes to the table, okay, the database behind the scenes needs to also maintain the indexes. So the more indexes you have, the slower the operation can potentially become. And as we've seen in this experiment, if you have big bulk loads into the table, sometimes you should consider dropping the indexes prior to loading and recreating them afterwards, okay? It might be actually faster to recreate the indexes after the operation than maintain the indexes throughout the operation. So now that we know the indexes are not always the best bet, not always the best plan, and that they are definitely not free, how can we identify those unused indexes, those dead weight indexes that nobody uses? So let's do a demonstration. Let's create a students table with ID and name and populate it with 10,000 students and create an index on the student ID, okay? Now, and that's interesting, we can fetch data about this index from PGStats all indexes. Remember that we talked about the information schema and said that there's a lot of useful information there? Well, here's an example. In this table, PGStats all indexes, we can fetch data for students IDIX, the index I just created, and there's a column here called IDX scan. This column indicates how many index scans were there for this index. So currently, there is 0 index scanned. Our index was not used yet. So let's use the index. Let's do explain analyze, select star from star where ID equals something, and we can see from the execution plan that the index is used. We can see an index scan using student ID IX, okay? If we go back to the table and do the exact same query, we can see that this time the number of index scan was incremented. So now we know that our index was used. So if you have an index that you suspect that is not being used, you can check this number. However, if you do that, you might run into a problem. You might see this number 5. And now to figure out if this index is actually used, you need to remember the number 5 and come back to check in an hour, a day, a week, I don't know. What you can do if you want to check a specific index is you can reset the counter. There's a function called pgstats reset single table counters, and it accepts the name, the actual index rel ID. As you can see, that's the second identifier from pgstats all indexes. It accepts the index rel ID for the index and resets the counter. So after resetting the counter for our specific index, we can see that index came back to 0. So now I can reset the counter, let my application run for a while, okay, maybe under normal load, and come back to check in a day, a week, a month. And if this index scan is 0, this index might not be used and can be dropped. So we saw how Postgres keep counters of the number of index scan and how we can use that to determine if an index is in fact used or not. However, I do want to share something that you might need to be aware of or be careful at. There are some situations where Postgres uses indexes internally that might not be logged in this table. So be very careful, especially around FK indexes, okay? Indexes on foreign keys when you determine whether an index really is used or not, okay? So probably for most trivial indexes that you suspect are not used, this is a very effective method. So now I want to talk a little bit about index bloat. I'm going to talk about bloat just in the context of an index, but this is also relevant for tables as well. So when we update something in Postgres, what's going on behind the scenes is maybe it's not very intuitive, but if you think that the database is going to the block and just overriding the value, then you'll be incorrect. What's happening when we're doing an update is that basically the old row is marked as deleted or as dead, and Postgres adds a new row, okay? This is how Postgres implements updates for both tables, and it also affects indexes. So these rows that were deleted are now marked as dead, and these dead rows cause bloat, okay? So bloat, if you think about it, like someone who's bloated, filled with air that needs to come out, right? So these dead rows cause bloat. So bloat affects both tables and indexes, and it can end up causing a lot of space. So the index can be very bloated, filled with dead rows, and consume lots of space. So there are several ways of releasing that bloat. So the first way is using something called vacuum, okay? So vacuum will not release the space back to the operating system, but it would make these dead rows available for new data. So if you got, added data and got bloated to 1 gigabyte in size and half of your index is bloat, running vacuum would release this dead rows. So as new rows are added, they can reclaim this data, which was previously dead, okay? So the index would not become smaller, but it will most likely not get bigger for a while, okay? So you can manually vacuum a table like this, vacuum table, and then Postgres will decide automatically which of the indexes on the table can benefit from actually vacuuming, from cleaning dead index tuples. Or you most likely, if you're not aware of that, you most likely have auto vacuum active in the background. So this is something that Postgres is doing. You can check if you have auto vacuum enabled. So just issue show auto vacuum. It should be on. If it's not on, you should consider turning it on. Okay. So with auto vacuum set to true, Postgres would automatically trigger a vacuum process once certain objects cross certain thresholds. Like once you inserted this amount of data as a percentage of the number of rows in the table, then auto vacuum will be triggered. Okay, so it's very handy. Another way of reclaiming space for dead rows and completely eliminate index bloat is to re-index the index. This will basically rebuild the index in place. Okay, so if you were unable to do re-index, what you had to do is to drop and create. So re-index basically does that. It drops and recreate the index. The problem with re-indexing is that it's a blocking operation. So while you re-index a certain index, other transactions can use this index for anything. And it may also affect the ability of other transactions to update, insert, and delete rows from the table. So that's no good. So for that, there's an operation called re-index concurrently, which means rebuild the index in place without acquiring too much restrictive locks, okay? So other transaction will be able to read, update, insert, and delete rows while you re-index the index. You should know that it takes more time and space, but it's fine because you can actually, you don't have much options on the live system. So now that we have a vague idea about index maintenance, let's talk about some common mistakes which I see a lot in indexes, okay? So one of the most common mistakes I see in index is to apply transformation on an indexed field. If you look at this example, if we select star from sale, where lower customer equals bill, the database did a sequential scan. Now the database has an index on the customer column, but because we applied a function lower on the column, the database was unable to use the index because the database does not have an index on lower customer. It has an index on customer. If we had a function-based index on lower customer, the database would be able to use that index, but we don't. So once we apply transformation on an index field, we potentially prevent the database from using this index. Another common example, which is kind of silly if you think about it, but if you apply arithmetics to an index field, it constitutes as an expression which may prevent the database from using the index. For example, if obviously we have an index on the ID field, but because we wrote the query this way, where ID plus 1 equals 100, the database did a sequential scan, was unable to use the index. But once we basically moved the literal 1 to the other side and did ID equals 100 minus 1, the database is now able to use the index and search for ID 99. Setting time zones is also a common mistake, which may prevent the database from using your index. So if, in this case, you have an index on sold at, once you did sold at time zone, that's an expression, and the database does not have this index, this expression indexed. So it may prevent the database from using this index. What you can do in this case is just move the time zone to the literal part, and that would enable the database to use the index. Date arithmetics with interval, also a very common mistake that I see. Instead of doing, it's very similar to the one we saw with the primary key, but this time it's date arithmetics. So sold at minus 1 day instead can just say sold at greater than some date plus 1 day. Just move the expression to the other side, and the database is able to use the index. Very important. Once again, casting. This is a very common example in site searches and login pages. You store the email in mixed case, and then you apply lower to find a matching email. Well, that's a very common mistake. What you want to do is you want to keep the email in a very specific case, so you can utilize the index. The bottom example is correct. If the email is stored in lowercase, then you can just apply the transformation on the literal instead of the potentially indexed value. Concatenation also, that's also a very common example I see in a lot of places. Instead of, you want to search for a full name. So instead of using first name equals Aki, last name equals Benita, you just generate this expression, and this will prevent the database from using any indexes you might have on first name or last name. So if possible, okay, you're better off with the second variation of this query. So to quick recap of this section, we start with a few misconceptions. Indexes are not always best. Remember the haystack example. Indexes are not always free. Remember the table with the 5 indexes, 7 times slower. We discussed how to identify unused indexes. If you remember, we used the information schema table and we reset the counter. We talked about how to rebuild indexes and reclaim space. We discussed briefly about bloat, how to reindex and now reindex concurrently. And then we saw a lot of very silly common mistakes that prevent the database from using the index. So that's it. Thank you very much.